this morning or yesterday for coming here in Sherbrooke. The auditorium is, well, full. It seems there's a few spaces left for people who are standing at the back if you want. I'm Justin Lefebvre. I'm the manager of the Quantum Algo Lab here at Institut Quantique, also chief officer at partnerships. And I'm very happy to have you all here for this, great day. Great lineup. We'll have, tons of very inspiring talks and panels during the day. And of course, some networking time as well. Let me introduce you to the scientific director of the Quantum Algo Lab, Stefanos Courtis. Stefanos is a physics professor here at Université de Sherbrooke, also the chair of Pascal chair in AI, and in quantum AI, in quantum AI. And Stefanos, if you want to have a few words for us.
Bonjour tout le monde. Good morning, everyone. Welcome to Sherbrooke. Welcome to Institut Quantique for this Applied Quantum Computing Symposium, the second one organized. I'm really excited just by looking at the program today. We already started with the first edition last year, and it was really nice to see enthusiasm and people embarking on quantum computing adventures. This year, as you'll probably see, the research that has started around this ecosystem here is a lot more mature. And so it means that things are moving at an exciting pace. So I'm really glad to see all of you today. And I'll get a chance later on also to talk to you with my researcher hat on. So.
And just because we didn't want to forget, to talk to you about the next events that we have. Usually people do that at the end of presentations or at the end of days, but people are tired. So we wanted you to be awake for this part as well. So let's see what is coming up in the next months in applied quantum computing and also, more theoretical as well. So for companies in the room or on the web that are with us today, next meeting is the SureHack 2026. It will be here in Sherbrooke in March. The final day it still has to be confirmed, but it will be in the second half of March. It will be the third edition of the SureHack. In the past two previous events, we had, about 10 companies who participated, something between 30 and 50 people in teams of 4. The morning is dedicated to learning about quantum computing, and the afternoon is really applying what's been learned in the morning to a challenge that is, given to you. And if you want to have more details, you probably already have Tom Mala's contact through the emails you received for this very specific day. So you can email him and you'll have all the details in due time. Next event is organized by the Quantum Algorithmic Alliance. Quantum Algorithmic Alliance has been founded by Institut Quantique, IVADO, and ETS in Montreal. And we are organizing our organizations this Canadian workshop on quantum algorithms. It will take place in April in IVADO's offices in Montreal at Métro Acadie. And it will be, so first day, April 27, will probably be dedicated to students, and then all PI students and hardware providers of quantum systems will be welcome to participate. So if you want to have more details about this, you can also, drop a quick email, and we'll make sure that you have all the details on this event as well. Next event, Stefanos.
Yes, so in June next year, June 7th to 19th, we'll have the second edition of the Algo Lab Summer School, which we have subtitled this year, Towards Fault-Tolerant Quantum Computing. So this summer school is addressed to grad students, postdocs, and also enthusiastic undergrads. And the point is to really learn both the principles of quantum computing, but also to program. So The Algo Lab team will have workshops, hands-on workshops in the afternoons, while the morning sessions are dedicated more to theoretical and fundamental aspects. We already have a really amazing lineup of lecturers for next summer. So if you're a student and you're interested, please keep this in mind. Also for the professors in the audience, please send your students. And then the next event for 2026 is a big one, TQC, perhaps the second biggest conference in quantum computing theory, quantum computation, and quantum algorithms, will be hosted here in Sherbrooke from August 31st to September 4th. We're in the process of planning this event. We anticipate a few hundreds of researchers, world-class expertise in quantum algorithms, quantum communication, and quantum cryptography to be in Sherbrooke next year. We're very excited about this event, so please put it on your calendars. And one last thing is, again, for the same reason that Ghislaine mentioned earlier, that usually we do this at the end, but I would like to take the opportunity in the beginning, while everybody's fresh, to thank all the people who put this event together, the Algo Lab team, the communications team at Sherbrooke, the technicians, all the staff that made this event possible.
Thank you. So to start this day, well, you know that Sherbrooke has been designated an innovation zone in quantum by the provincial government a few years ago. And well, the innovation zone now has a new director for a few months now, Michel Pirot-Ladrière. Well, Michel is with us this morning to talk a little bit about, well, what's new in the innovation zone and what is exciting coming very soon, like right here in Sherbrooke. So, Michel, the floor is yours.
I will start again. I'd like to join Stefanos, where is he? Here, and Ghislain in welcoming you to the 2025 Applied Quantum Computing Symposium. So I'd like to start by saying that today we are gathered to answer a very difficult question, actually. So how can we make quantum computing useful? This question, as you know, has two sides. The first one is, how do we make the hardware work? We saw already in the titles of upcoming events that there's a big challenge. It's quantum error correction. So how do we address this challenge? And here, right here in Sherbrooke, we have major hardware companies that are the cutting edge, like IBM. There's someone from IBM. Justin, where are you? There, okay. Quantic. There's someone from Quantic. Pascal, Equal One will also talk today on the panel, and several more are interested in joining the zone. And I think today you are also gathered to answer the other side of the question, is once we have a working quantum computer, what can we do with it? This is a very important field of research. And I'd like to highlight one of the talk of today by René Kouarfate on the reserves in property and casualty insurance. This highlights the importance of the collision of ideas, and Institut Quantique it's one of their role is to put people of different fields together and come up with new solutions. In this particular example, it's mathematics and insurance. This is amazing, and we need to do more of that. As Ghislain says many times, the biggest quantum advantage today is talents. And here in Sherbrooke, you have access to a lot of talents. And today is an example. I think we have who are students here and research. Excellent. And I think we also have students from the Quantum Computing Bachelor program. in here? Please raise your hands. Excellent. Okay. So this is the first Francophone bachelor degree to train quantum computer scientists. And then the idea is they can, at the end of their bachelor program, work. Don't have to do a PG and a master if they don't want to. So what's our job at District? Well, it's very simple. So at District Sherbrooke Quantum Innovation Zone, our job is to make sure these talents succeed. A few years ago, not so long ago, it was great to study here at University of Sherbrooke, but then you had no jobs to go. You had to go worldwide, and if you wanted to become a prof, you can end up anywhere in the world because the probability is very low. It's only 5% of the job market. So right now it's very different. Students here, when they graduate, they can walk down walk down this path, go to the river, and they have jobs, very high-paying jobs in quantum technologies. If you go down the road, you will be amazed to see at lunch at Espace Quantique 1 how many alumni of Institut Quantique are now there. And they are not just working there, they are changing the world by funding world-changing companies. And there's a catalyst for that. We have Bouraoui here, the QV Studio. So District, our mission is actually very simple. We are building the city of the future. And it's along the river down there, okay? And we have already a very good success story. So we have built Espace Quantique 1, and this is a space where you can grow your idea all the way to an established companies. So for those who are interested to start a company or work at the zone, please let me know. We are there to help you. I wish you a very successful symposium. Thanks.
Merci, Michel. Good. Well, thanks a lot, Michel, for this introduction to District and for people who are not from Sherbrooke or even for people that are from here. If you've never been at Espace Quantique 1, it's really worth it. I encourage you to go there and visit and see what's proposed. Let's start now with the, well, real exciting stuff of research. We are very happy to have today a keynote speaker from Université de Montréal and also at Mila and Ivado. He's assistant professor in computer science working a lot on quantum algorithms. Please welcome Claire Christiansen for this keynote.
Thanks. Okay. Hi. Bonjour. Merci beaucoup pour l'invitation, and thank you very much for inviting me to come here. And I'm very happy to be back in Sherbrooke again for the second time to give a talk. Can you hear me at the back? Okay. Okay. So today I'm going to present an overview of my research directions and my research program, which is about functional programming and causal structure in quantum computation. So in this talk, I will try and give an overview of this general research area, how it's being carried out in general, and I will mention some of topics that I've worked on myself as well. Previously, both at those institutions at the top, including current collaborators there, and then what I'm currently working on in Université de Montréal and Mila. This one is supposed to work. Okay, thank you. So since it's the first technical talk of the day, I guess I should explain very briefly about why quantum computers are useful and why we should care at all. So I guess most of you might know this already, but I want to just highlight some of the key motivations from my point of view. So quantum computers are devices that harness quantum physics to do information processing. And they can't do everything, but they can do very specific things very well, or at least we hope that they will do once we've built them. So one such thing is to solve specific problems much faster, so super polynomially faster than any known or existing classical algorithm, or potentially even faster than any possible classical algorithm, such as Shor's algorithm for factoring large numbers. And maybe most interestingly, I would say that quantum computers could be used to simulate nature, to simulate physical systems at the quantum level. So that is molecules, atoms, and so on. And this ability we expect to have the potential to revolutionize things such as materials or drug discovery in the future. Although, of course, the actual industrial applications are very far away now. So hopefully, you know, by talking to industry and building up an ecosystem of academia and industry, we'll be able to actually try and understand where the potential there lies. And finally, like machine learning is a really current technology, and combining the advantages of machine learning and quantum computing is something that's been a very active area of research in recent years. So now we know what quantum computers could do. Let's ask why we don't have them, ready to go to do all the amazing things that have been promised to us on the textbooks. So there are several. I would say there are like 4 main challenges that we face currently today in getting to a place where we can deploy quantum computers in industry. So the first one is actually building the experimental systems. So as building quantum computers with large enough number of qubits to be able to actually solve interesting problems. And that's a really hard challenge because the qubits typically they decohere and turn back into classical bits. When you put them basically when you put them in the lab, they will typically decohere unless you find advanced ways to control them. So I think there's very cutting-edge research being done right here in this building on this topic. And even once we've built those computers, there's a kind of a trade-off between building a computer with really good qubits, but also, you need to still correct the errors, and so we need to design efficient error-correcting codes to further enhance the possibility of using the qubits that we've built, even though they may have noise. So that's a very active area of research as well, defining the error-correcting codes and go on top and turn the physical qubits in the lab into logical qubits that we can actually do computation on noiselessly. And once we have those 2 things, we need to build reliable communication networks that allow us to transfer this quantum information between distant quantum computers or between different parties that are interacting in a quantum way to avoid, again, the information decohering back from qubits into classical bits and thus losing any quantum advantage. But even if all of those engineering and practical and communication challenges are resolved, actually we haven't really got a killer application for quantum computers yet. There are, apart from a very, very few specific instances, such as Shor's algorithm. So there's still a lot of work to be done on the theory side to take the kind of basic building block algorithms that have been shown to have some significant superpolynomial advantages over classical algorithms and turn them into full stack end-to-end applications that allow us to deploy some algorithm on a genuine use case in industry and show that the quantum application of the algorithm will beat any existing or even potentially any possible classical algorithm. Now, to do this, I argue that we need to not only focus on sitting down and building algorithms, but have to continue to do foundational quantum research, which is because it is precisely the properties of quantum physics that are interesting to us, that are really strange and counterintuitive and different from the classical world, that are the same ones that lead to advantages in quantum information processing. So I argue that building algorithms for industrial applications will need to continue to go hand in hand with foundational research in quantum physics and quantum information. So in this talk, I will give some ideas on my own perspective on where I think are interesting questions to look at this intersection. So, in my own research, I am interested in building what we call a functional programming paradigm for quantum information processing. And the motivation of this is to introduce a notion of modularity in quantum computation. So classical computation is fundamentally modular. So I can write a function in Python today, and you can write another one tomorrow, and then someone else can come and concatenate them together in any way they like next week without having to know the internal structure or the physical implementation on hardware of those functions. They can just do that at an abstract level and the level of functions in a high-level programming language. However, currently in quantum computing, we are still really designing algorithms most of the time at the machine code level. So we'll start with some quantum states, which are like variables in classical programming, and then you apply a sequence of logic gates or quantum logic gates analogous to the classical functions that we apply on variables. And you apply them in a sequence and you get an output. But right now, we don't really have too many ways, or not, at least not until very recently, we haven't had ways to think about quantum algorithms from the point of view of functional transformations, of functions that transform other functions, and so on. So in my research, I hope to kind of re-establish this notion of modularity in quantum computation, as it has been extremely useful and kind of a fundamental part of classical computation for the last few decades. Now, additionally, this notion of quantum functional programming, we've shown it to be useful for quantum communication, to enhance the ability to do communication. And we've shown that it can lead to new ways of performing simulations of physical systems at the quantum level, which may have potential implications in the molecular simulations. Similarly, we believe that this could have implications for quantum machine learning architectures and explainability, which is linked to the fact that the structure of functional programming in quantum computation is also fundamentally linked to causal structure in quantum physics, which I'll briefly describe at the end. Okay, so can I just check how long do I have for the talk? Because 20 minutes. Okay, so we're at this one, 10 past. Okay, perfect. Okay, so again, since it's the first technical talk, let me very briefly, in about 2 minutes, explain quantum computing. So I taught my students this semester 30 lectures of quantum computing, so they'll be very sad if I teach it to you in 2 minutes. But I think actually the quantum computing is not that complicated at the basic level. You can do everything in 2 slides. So basically, classical computer has a state at any given time as given by bit string, like 0, 1, 1, 0. Quantum computer is more or less the same, except now bit strings become qubits. Qubits are vectors in what we call a Hilbert space. It's just a complex vector space with an inner product. And they're denoted with these angular brackets. So each distinct bit string becomes a distinct vector, orthogonal vector. So every bit string becomes a vector that is orthogonal to every other vector made from another bit string. So here, like the quantum state 0, 1, 1, 0 is orthogonal to 1, 0, 1, 1, written in this angular brackets. But since they're vectors, we can add them together to form what we call superposition states. So we can now have superpositions of different vectors, which are just linear combinations of vectors with some coefficients alpha and beta, which can be complex. And they are normalized in a way that the square of their modulus is equal to 1. And now the point is that to get back some outputs, to get back some classical output at the end, like the original bit strings, we can perform a measurement, and then the measurement returns the classical bit strings with probability equal to the square of those coefficients alpha and beta. So that's very simple. You just take the bit strings, turn them into vectors, and then you get quantum computing. And that's the state. And now, states on their own are not interesting because states have to do something over time to actually do computation. So again, we can think about functions of states. So classically, a computation is just any function on bit strings. So we call them logic gates, like NOT, XOR, NAND, and we can draw them as a circuit like this. So for example, here I start with a bit 0, goes for a NOT gate, becomes bit 1, and there's an XOR gate, blah, 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 so on. Quantum computing is more or less the same, except now we need to have reversible operations. Instead of any possible logic gates on Booleans, we have any possible reversible gate on a Hilbert space, because that's the state of the system was vectors in a Hilbert space. So now we have any reversible operation on the Hilbert space, and that is precisely what we call the unitary matrices. So these are matrices called unitary matrices, and they just map one vector to some other vector. And the vector it maps to has to have the same norm, and it could be a linear combination of other basis vectors. And again, we can draw it as a circuit. So that's it. So that's basically the essence of quantum computation. We have states states are qubits, and the evolution or the dynamics of states is given by unitary matrices. So now let's move to motivations of my own research directions, which is quantum functional programming. So let's start by contrasting this with standard quantum computation, what is typically done now in the design of algorithms, which is we have some quantum state, some qubits, we have some functional quantum states, which as I just told you is a bunch of unitary matrices, and the output is going to be some new quantum state, which is just those unitaries, which are written as quantum gates. They process the quantum state and they give you a new quantum state. So in this sense, quantum computers are used as quantum state processors. And now we can ask, well, what about functions of functions? So I have functions of states, but is it possible to have functions of the quantum gates themselves? Well, then the picture will look like this. So I have some first order function, which is like the unitary matrices that I apply to the states. But now instead of using that to compute states, I consider a higher order function g that computes something on the space of possible functions. So input to the quantum computer will be first order function f, higher order function g, and then the output is going to be a new first order function, capital G of f, which describes the action of this, what we call a higher order map on the unitaries or the quantum gates more generally. In this way, quantum computers are used as quantum function processors. And this brings quantum computing in line with best design principles in classical computation. However, we have a problem, because computation on black box unitary gates, the things that do computation in the quantum case, is in fact severely restricted. So, if I want to have a function that computes something on first order functions, the unitary gates, then of course that big higher order function g needs to be able to act on the whole space without knowing the details of the physical implementation of how you've engineered such a gate in the lab. But such computation turns out to be incompatible with the laws of physics in many cases. So just naively taking some higher order function and saying, okay, for any input unitary u, I'm going to give you some function of a unitary. For example, the inverse of a unitary. That's actually against the laws of physics. You can prove that it's impossible. So we need to find ways to kind of get around this, and that's basically the whole thing, the whole kind of crux of this research program. So for example, as I said, there does not exist any universal higher order function g that for any input unitary matrix u outputs the inverse of the matrix. In the classical case, this is trivial. Given any function, you can just compute its inverse directly. But in the quantum case, it's not possible. However, a work by my former colleagues at the University of Tokyo showed that, in fact, if you have for qubit unitaries, if you're able to have 4 copies of the same unitary and you can use it repeatedly, then you're able to make both deterministically and exactly another copy, a single copy of the inverse of the unitary. So now we exploit using multiple calls, querying multiple times the input unitary that you want to transform, and that allows you to perform such transformations. And this the kind of the construction of these inverting unitary transformations is actually has been a large research program over the last decade, and there are several other works in this topic. Another similar problem is the control or quantum if statement of quantum channels. So quantum channels are actually basically the noisy version of unitary gates, and you can prove another no-go theorem that if I want to make a if clause, a quantum version of the if clause. So let's say I have a quantum channel A and another one B, and I say, okay, if some control qubit is in the state 0, I will perform channel A. If it's in state 1, I'll perform channel B. But in a quantum way, so that if the control is in some superposition state 0 plus 1, I will perform a superposition of the gates A and B. So that's kind of the quantum version of the if statement. Impossible, sadly. But if I can't even make an if clause in quantum computing, then it's not very good, because that's if you ever learned programming, like in your first year of a university, probably the first thing you learned is the if clause. So if I can't even do that in the quantum computing, then the idea of functional programming kind of goes out of the window. So we should try and work a bit harder to do that. And in fact, it turns out that there are some ways to implement an if statement of quantum channels if you have additional information about a specific part of the implementation of the channel. So you don't need the full implementation, but if you have a very specific understanding of the physical system that you have, then my collaborators and I, during my time in my PhD at the University of Oxford with collaborators at the University of Hong Kong, we found and developed a protocol for controlling universally arbitrary quantum channels. Okay, so I just showed you two examples of like basic operations that we might want to apply, like inverting quantum gates and controlling quantum gates is an if statement. So those are the two kind of basic operations. But the whole point was to illustrate a more just simple examples of a more broader phenomena, which is functional simulation now in the context, let's say, of some complicated dynamics of a physical systems. So we can take this further from the simple examples and really now try and do functional simulation of the gates that describe actually physical system, quantum system evolving in time. So at the quantum level, all physical systems are described by the Hamiltonian dynamics. So every unitary that describes the evolution of a physical system is not just a gate, on a page, but actually it's described by a Hamiltonian, a Hermitian matrix H, and basically the system will evolve according to this unitary operator, which is e to the minus IHT, where t is time. So it's very hard to simulate the Hamiltonian on a classical computer because the Hamiltonian H can be a very big matrix, and in fact the size of the matrix scales exponentially with the system size. But a quantum computer can directly encode the state of the system. And so you would expect that just this kind of difference in the system size would allow you to, or the kind of the scaling of the encoding process should give you some advantages in a simulation in the quantum case. And in fact, there's been a large number of quantum algorithmic research basically solving this evolution problem. So given some classical description of a Hamiltonian H, so you write down the matrix H, like maybe is like 1,000 entries by 1,000 entries matrix on paper, and you want to calculate how it actually acts on a quantum state. So you want to simulate its evolution. That's the e to the minus IHT for some time t. So there's been a lot of work on this, many state-of-the-art algorithms. But here, using the functional programming approach, we come up with a new idea, a new way of doing simulation, which is, the question now is given black box access, so, maybe in the lab we don't always have the H written out for us in the 1,000 by 1,000 entries. Maybe we just have in the lab, over there, we have some box and we have some system evolving in time according to its own internal physical dynamics. And now the question is, if I have access to such a device in the lab that's evolving, but I don't know what it is, I don't understand what it's doing. Can I apply some quantum gates directly on the system to simulate a functional transformation of the Hamiltonian? So can I let the Hamiltonian itself transform, from h to some function f of h? And what does it mean to transform a Hamiltonian? Well, the Hamiltonian encodes, all the information about the system, about the energies, couplings between different parts of the system. So transforming the Hamiltonian corresponds to taking a molecule in the lab or a solid state system and transforming it into another molecule or another solid state system. Basically, essentially, you can use one physical system to simulate how another physical system would evolve. This line of research is also related to another line of work you may be familiar with called the quantum signal processing, qubitization, or QSVT. Those three are more or less the same direction of work. And I'll just briefly mention a bit later the connection. So in the series of works with my collaborators at the University of Tokyo, where I did a postdoc in collaboration with IBM, actually, where we showed, we developed a number of algorithms. First of all, we developed a universal algorithm that takes any Hamiltonian and transforms it by any linear function f, which is deterministic and approximate with error, and the algorithm, runtime of the algorithm scales quadratically with time and linearly with 1 over the error, which would be considered a good, but not yet maybe optimal scaling. And this algorithm can be used to actually probe and understand parameters of the Hamiltonian. So this is kind of related to another field called Hamiltonian learning, which is about learning what the system in the lab is doing. So using this algorithm, so given any Hamiltonian H that can be decomposed as a sum of n-qubit Pauli matrices. So if we have some coefficient Cu, we can learn these coefficients of the Hamiltonian in time that is proportional to the logarithm of 1 over the failure probability and 1 over the precision, which is, you can prove is optimal scaling, which is called Heisenberg limited scaling. It's the best possible scaling you can get, so fastest way of learning those parameters. So that's really nice that, we can use this functional programming approach. We get a way to, from one material, we get another one, so to say, but we can also use this same mathematical and functional structure to even just learn the Hamiltonian, to understand what the thing actually is in the lab. And the second algorithm we derived allows us now to transform not just by any linear functions, but actually allows us to transform a Hamiltonian H by any function f that's sufficiently differentiable, which we do by basically transforming the eigenvalues of the Hamiltonian. Now, the eigenvalues of a Hamiltonian correspond to the energy levels. And so the energy levels typically describe most of the interesting behavior of a Hamiltonian. So this algorithm takes any Hamiltonian H, it has some energy spectrum, and it allows it to shift the energy spectrum by some function, even though we don't know what the original energy spectrum is. And that's really nice because it can take a complicated Hamiltonian. Let's say a very hard Hamiltonian in the lab. You don't know what it is. It's a complicated spectrum, and you can just you could simplify it and just shift the energies all up and all down, for example, to make it into a simple Hamiltonian that you can use to maybe even use it to find the ground state energy of the Hamiltonian. This is possible with the algorithm, although the scaling we haven't yet completed kind of a full calculation to see if we can make this scaling optimal or close. But conversely, you could use this algorithm to start with a simple molecule that you might have in the lab and use it to simulate a more complicated molecule, or a Hamiltonian describing the molecule that you don't know how to build yet. And finally, a master student in UDM, Marek Arsenault, who's working with me, is currently finding the equivalence, or I think he's kind of shown certain equivalences between this whole framework of higher order algorithms for transforming Hamiltonians and the recent direction I mentioned earlier called quantum signal processing, namely specifically a generalized version called the generalized quantum signal processing, GQSP. So if I give another talk next year, then we'll have some new results in that direction, which is a really nice equivalence between two recent state-of-the-art frameworks. So just to explain how this algorithm works, so basically the gist of all these algorithms that we develop for Hamiltonian simulation functionally is that you have some physical system in the lab, you evolve it in time by some short time intervals t over n, and you do that n times. And then there are some fixed gates, which are shown in blue here. And so you basically alternate the evolution of your fixed Hamiltonian in the lab with some gates in blue that you make yourself and design based on the function f. So given any function f, you kind of get you design the blue fixed gates in the lab. But then you can input any free Hamiltonian evolution that you like, that you don't know what it is here, that are depicted in this molecular structure in the picture. And then the output will be that function f that you are given, acting on the unknown Hamiltonian h in the lab. So from any unknown physical system, you can simulate a new one. And one application of this is simulating the negative time dynamics. Let me see, 5 minutes? Okay. So any physical system typically will evolve in time according to its Hamiltonian. So after time t, it will evolve and change in its base. It will change the state of the system in a certain way. And using this algorithm, we can just take the function h, function f of h to be minus h, and that allows us to simulate the time evolution in the opposite direction. So given a molecule or a material that is here evolves in time, now I'm here, using my algorithm, I can discover how this system was, how it behaved, even before I started the experiment. So going back to where I started, before I even was able to look at it. So this reversal time is like very interesting from a fundamental point of view, because I really reversed the direction of time, the travel of time. But interestingly, from a practical perspective, is that we actually have a modified version of this algorithm specifically for this function f that inverses time that does not require any auxiliary qubits. And that means that it's kind of possible, at least in principle, to apply this algorithm on existing laboratory equipment. And so we actually have two experimental collaborations trying to verify this. The first one is about the algorithm. So we started an experimental collaboration in the University of Oxford to try and just implement the whole algorithm on a superconducting device. Of course, in that case, we'd have to actually know h in order to build it on a superconducting device, but just to prove that we can do the algorithm. And secondly, we're exploring a proof of principle more generally to just be able to apply any transformations on genuinely unknown physical systems in the lab. So if I have a genuine H that I don't know in the lab, for example, in this ultra-fast spectroscopy kind of lab, then we're trying to see ways that we can actually transform the H using the devices that they have. We may not be able to get to all the complicated algorithms like inverting time, but at least we're trying to see how much we can do, how we can perform functional programming on an unknown device using such spectroscopic or similar systems. Finally, in the last 2 minutes, I guess, I will mention why this is also related to quantum causality. The point is that causal relationing is an important topic in statistics, machine learning, and so on, separating causation from correlation. The problem is that the structure of a causal structure and causal modeling cannot directly be generalized to the quantum world, but it requires a specific concept known as quantum causal models. And maybe to just save the kind of punchline is that it turns out that the quantum causal models are fundamentally described by these same higher order quantum transformations, which are the transformations from quantum gates to quantum gates. The same thing as we've just been talking about for the last 10 minutes in quantum functional programming. So, and it turns out that using this framework of quantum causal models, you can study the causal structure and also explainability from a causal point of view of quantum processes, which is several works that I did during my PhD in Oxford and also other works by my collaborators and other authors on similar topics. And so this leads to a question about how we could maybe use causality, use higher order functional programming to understand the causal structure in quantum algorithms or even in quantum machine learning. Okay, so to summarize, quantum computing has the potential to revolutionize computation in various areas, including a simulation of physical systems. But what we really need now, in addition to building the devices, is to develop really great and powerful industry-relevant applications. And one such direction, which I personally believe is very promising, is the functional programming quantum computation, also known as higher-order quantum computation, that brings quantum algorithm design in line with its classical counterpart in order to do modular functional concatenation. This allows us to do this functional simulation of quantum systems, and it also gives us a way to describe causal structure, a really foundational concept that is also recently practically applicable in various industrial areas in quantum theory. And in the future, we hope that this could allow for the functional simulation of new full material properties, or even a better understanding of causal reasoning in areas such as quantum machine learning. So with that, thank you very much for your attention.
Thank you, Claire. And I guess that just because of, well, this very tight schedule we have, we will move to the next presentation. But if you have questions for Claire, of course, well, next break is coming soon. Otherwise, on lunchtime, I guess you will be around and ready for questions. Yeah, fantastic. Well, thanks a lot for this great presentation. Our next presenter will talk to you about variational quantum state preparation. He is professor at ETS Montreal, also MEIE chair and director of the Institute on Quantum Science and Technologies at ETS. Please welcome Jacob Biamonte.
Bonjour à toutes et à tous. Do you think there's any way to switch that so it works?
To enlarge it?
Yeah.
Where's the control? It's just reflecting your, it's mirroring your tablet right now. Where's the actual presentation?
Well,
or it's a drawing?
this is a modern version of a chalk talk. It's actually very elegant if it does work.
Sure.
If it does not, it'll be quite embarrassing, but I'll pivot. Okay? In fact, I could use real chalk. In fact, yeah, this will bring me back to my roots before the tablets emerged and ruined our lives. In which case, we have to locate the chalk. So you can imagine the state of affairs when there's no chalk, but there's PowerPoint. And you would imagine that thank you, sir. Weapons in place, the talk shall commence. Bonjour à toutes et à tous. Je voudrais vous dire, merci beaucoup, l'équipe d'organisation. Je vais changer en anglais. J'étudie le français encore. Je suis encore intermédiaire approximatif. So, quantum computers really just do one thing. They prepare states. Okay? And so we have this opportunity to prepare states using quantum computers. And to do that, like every PhD student, you have to have a theory, okay, to test, to validate. So our theory begins with a variational principle. And what we have is we'll say, we're going to take a Hermitian matrix, H. Oh, so beautiful. So this is the set of complex Hermitian matrices of size n by n, okay? And for this variational principle, we're going to say that n is non-negative, or in the language of physics, which I don't like this, positive semi-definite. Don't say that. Non-negative, it's enough. Oh boy, that was a, do you see that? It's chaotic, yeah. So we'll write this with this little curly thing, and we'll say that that means that H, this is your Hamiltonian. So for those that don't know H, and this is the real challenge, you have to give a popular chalk talk, okay? So a Hamiltonian governs the dynamics of your physical system, and we're talking about a static configuration with this, and you can implement those in different ways. So this one will have the non-negative property, but in addition, the kernel of H will be constricted to the linear span of some vector, let's call it 0. Okay, so that means it has a one-dimensional kernel, and that means when the free energy or whatever other process minimizes this Hamiltonian, you have a unique configuration as its ground state. Moreover, in the finite dimensional limit, we'll say that the perpendicular space, and we'll write this in kind of this silly way, the perpendicular space will be greater than or equal to some value delta, and this is some constant that's greater than or equal to 1. And what that means is that your physical system is gapped, okay? So you're not in some kind of transition between, let's say, ice and solid or ice and liquid. You're gapped, okay? So this is condition 1, this is condition 2, this is condition 3. Now condition 4 is that you somehow magically are given this state, phi, and everything's normalized whenever we work with physics, so we just skip writing that part because it's annoying, but this is a unit norm state. We're given the state phi, or, now that's a disaster. It just ruins all, the photo's ruined. It's like your life is over. It's like a tattoo you can't get rid of, right? Okay, so let's say that there's exists a state rho such that rho h is less than delta. So this is given to you by above. Merlin comes down and says, we provide you this state, okay? Now later we're gonna replace Merlin with a lot of talented coders, okay, one of which is sitting there. But for now, if we have that, we have something that is called the stability lemma, okay? So the stability lemma, actually it's a very fun thing. It's a very fun thing. So these things, all 4 of those, they'll imply this. They'll imply that 1 minus, and we'll use a little bit of notation here. I'm just gonna write this as h, the expected value of h. 1 minus the expected value of h over this gap, okay, is less than or equal to the true ground state overlap with the thing you prepared. Let us review. This is a variational principle. It's very important. So I can measure expected values. In fact, there's a subtlety in DiVincenzo's criteria because he says he wants individual qubit readout, but in fact, you only need that for some cases, and you don't need that to get something that is QMA hard, actually. This is another point. So all you need is expected values, but this is another discussion. And this, why this? Because I can measure this on IBM, I can measure this on Pascal, right? Not me personally, they wouldn't let me, because you have to use the online system. And for that, you have to go to Pink, and even with that involved, it will still take time, but it will happen eventually. This I can measure. This is the ability to approximate this thing I'm trying to prepare, okay? And this comes from the variational principle. In fact, one track of research that we're working on is we say, okay, well, how tight can you make this, right? How tight can you make this? And you can do higher order powers, and one of the research questions we're looking at right now is we say, okay, when the power becomes high enough, okay, at what point will this become exact? Okay, so we can go into that a little bit later, but this you can measure, this is what you want, and the question is, what are we gonna do with it, okay? So, in fact, most quantum algorithms that are being deployed today follow some form of a variational principle. Okay, one example would be, oh, I have this chemistry molecule, and for some reason I wanna know the low spectrum so I can get some kind of excitation energy. We just saw some of that in the prior talk, which was quite good, by the way. In this particular case, we decided to start off with something that could possibly involve taking a record, okay? And we wanted to take the record away from IBM on their own hardware. This didn't work. And we probably need their help to go a little bit further, but I'll tell you why it didn't work. And the reason it didn't work is actually interesting. So let me go into the theory. So this is a variational principle. Now, what operator are you trying to minimize? Okay, so I have to now reverse the question that I'm normally given. So normally in quantum computing, they say, here's an operator, minimize it. Right? In fact, the entire research program of quantum computing is this weird trial and error thing where they think somehow they're going to just find this magical operator that you can minimize, but classical computers cannot. Okay, so that's not exactly what we're doing. We're actually flipping the problem around. We're saying, look, we have this, okay, and we want this thing that satisfies that. There's a number of different ways to do it. These things are called parent Hamiltonians. And the simplest parent Hamiltonian, I will show you now. We say that H is going to be equal to, let's say, a summation over L equals 1 to N. And you can have these projectors. And anything you write, I'm going to write it a little differently. I don't know why that is, but my way is always better. Okay? That's the rule in life. So you write this down, and this one's very easy because we know the spectrum. We know everything about this Hamiltonian. It's like the easiest Hamiltonian. Okay? It could even be your favorite Hamiltonian. We say X is some bit string. So it's some bit string, and we say H on X is just equal to the 1 norm of X. It just counts the bits. Okay, so I know everything about this spectrum, and I can check my conditions. The ground state energy is 0. Okay? Everything else is non-negative. The kernel is one-dimensional, and it is gapped, right? It is gapped. It has a gap. So you satisfy the theorem with this. Then you can evolve this in the Heisenberg picture, and you can say that H twiddle is going to give you some quantum circuit, U, H, U dagger, at which case the ground state of this Hamiltonian, H twiddle, can act on U0, which equals 0. This is the output of the circuit that you're trying to optimize to find. Yes? 5 more minutes. And just as it gets started, it comes to a conclusion. It's always the way life is. You know, it's so finite. It's like if I really thought I'd have a chance to live forever, I'd drop all this quantum stuff and go to a lab on longevity, but I think it's impossible, so I just stick with physics, you know? So we get a Hamiltonian out. Now here's the trick with this one. This is a tricky part. Right there, your cardinality of your operator can blow up. What do I mean by that? The number of Pauli terms in your string. Okay? But there's something magic that happens when this is a Clifford circuit. The cardinality will be fixed. So Clifford conjugation acts as an involution on the set of Pauli strings, okay? Which means one Pauli string uniquely goes to another. You don't get 2 Pauli strings out. So that right there gives you a very big class of stabilizer Hamiltonians. The problem with that is stabilizer states are fairly easy to measure because you can just measure all the stabilizers, okay? So we stuck in the magical GHZ circuit. Okay, we had all of our stuff working. We get out this kind of cool Hamiltonian. It looks something like -1/2 summation of L, L plus 1, Z sub L, Z sub L plus 1, and then it had like another -1/2, L equals 1 to N, X sub L. So this part's non-physical, this part's physical, but you can measure all of this and you can minimize this thing and you check it and you get like the GHZ as a ground state. Now here's where it gets interesting. So we got these guys are super smart, okay? They don't actually listen to me because it involves things that I don't know about, okay? So we have other people here that they listen to, and what they do is they program quantum computers. Like I also program quantum computers, but let's say that they really program them. And we said, okay, let's use a variational outer loop and let's go after these world records for state prep right in Quebec. And here's the problem. I'm old enough where the T1 time used to dominate and the measurement error was so extreme that in my mind I had this model, because this is all the theory, but then there's a conjecture. And the problem is the circuits to prepare GHZ are too short to really dig into the modern T1 times. So you dominate by gate errors. And if you compress the circuit, the number of gate errors goes up. And that becomes a dominant factor. And there's one more problem with the GHZ state. It has these stabilizers. These things can be measured, and you do what's called post-selection. So you prepare an ensemble of states, and you throw away the garbage, okay? So for example, on a GHZ state, if you see a 0, 1, you toss it. And then the worst part about it all was they came out with a paper with a 140 qubit demonstration, right as we're finishing this up, and we're like around 36, okay? Which is about half the world record. But what they didn't see coming is we can switch our state. And so where we are now, and I like to do this because part of it is like if it's interesting, you can talk to us about it. So where we are now, we want to understand the trade-off where gate error becomes less significant than T1 time, because T1 time is pretty bad. It's exponential, but you gotta get out a little bit first. In that regime, barring post-selection, all these other tricks, in that regime, you'd think the outer loop would actually be able to help, okay? And so tomorrow, we'll hear from Antoine, okay? Yeah. Where's Guy Philippe? Guy's in the back, okay, we'll hear from Bacombe. Where's Pacombe? He's still trying to park? No, he's here, he's out there. We'll hear from Robin tomorrow, okay? We'll hear from a number of different people. We'll hear from Ernesto at some point. And we'll hear these results, and we'll see these results, and we'll say, okay, is this theory gonna work? We think so, we're predicting it. This is the conjecture. Are we gonna take a record? It's fun to try. I think we'll get it. It won't be for GHZ, because they kind of, they did an incredible experiment recently. I don't know if you guys are aware of it. We'll also talk about that a little bit. So in any case, I apologize for the technical dysfunction, but I think in the end, it worked out fine.
Thank you very much, Jacob. So for our next presentation, we have Tao Zheng, Associate Professor in the Department of Chemistry at York University, going to talk about quantum seniority-based subspace expansion, linear combinations of short circuits, unitary transformations for efficient quantum measurements. So, Tao, the floor is yours.
Where's the pointer? The pointer.
This button, you have to keep it.
Okay. Good. Good morning. Thank you for giving me this opportunity. So my name is Toby Zheng, and I'm from York University. But currently I'm visiting Professor Ismailov's group at University of Toronto. So the research I'm presenting comes from our collaboration. It's not moving on.
Yeah, it is.
Okay. So the central problem that we solve in quantum chemistry calculation is to solve the Schrodinger equation. But in classical computing methods, for instance, using configuration interaction, then we face the intractable exponential scaling of the problem. As the size increase, the number of bases that increase horribly, and then eventually the calculation won't move on. And then this dimension problem can be solved using quantum computing. For instance, we eventually have only one state, ideally, in the variational quantum eigensolver, a formalism, and then we prepare the state using a circuit and then apply the long circuits onto the reference states, and then we can optimize the circuits, and then we can have the lowest possible ground state energy. But we have unfavorable error scaling with respect to number of states, number of gates, and at the same time, there will be high sampling costs for optimizing the parameters of the circuit as well. So the problem of the original dimension has only been translated into the gate problems or measurement problem. So is there any way to trade off the two ends? For instance, we have a smaller number of states, we have a shorter dimension, but at the same time simpler circuits. Yes, it's possible, and then the quantum subspace eigen subspace expansion is the possibility. So this QSE is usually used to solve the generalized eigenvalue problem, HC equals SCE, and then starting from a common Hartree-Fock reference Slater determinants, we perturb the states using unitary transformation operators, for instance, J or I, and then to create two basis functions, and then those states are prepared using quantum computer, and then the Hamiltonian matrix elements and as well the overlap matrix elements are measured using quantum computer as well. And once they are measured, they are fed to a classical computer and then for diagonalization. Now, we have simpler circuits, definitely, because part of the complexity has been translated into the dimension now, because we don't have a one dimension, we have actually a matrix now. But at the cost of what? We need to measure more matrix elements. Compared to a quantum eigensolver, we have only one element, we have only one state, but we have many states now. And then we need to measure the matrix elements for more of these states. And also we need to measure off-diagonal matrix elements, so which involves more ancillar cubics, and then the measurement cost and also the accuracy requirement is even higher. And the last one is the non-orthogonality. So now the matrix elements between the basis functions are not orthogonal to each other. They're non-zero, which means that the matrix, they are ill-conditioned, and that imposes higher requirement on accuracy. So with the simplest circuits, it is in exchange of three problems, and they are all related to measurement costs. So how to solve the problem? We propose an idea to solve the problem is to use the artificial symmetry. So what is artificial symmetry? Symmetry are the operators that commute with Hamiltonian. But now we have some symmetry operators that do not commute with the Hamiltonians. They are Hermitian, they do not commute with Hamiltonians. And then we use the eigenstates of the symmetry operators as the basis to resolve the Hamiltonian. And now, the basis functions with different symmetry eigenvalues, they are orthogonal to each other. So the non-orthogonality problem has been solved. So the measurement cost coming from ill-conditioned matrix has been lowered. On the other hand, the symmetry operators do not commute with Hamiltonian, and therefore the off-diagonal matrix elements for the states with different symmetry eigenvalues, they are non-zero. But at the same time, the terms within the Hamiltonian that really connect the Bryan cat with different symmetry eigenvalues are limited. Not the whole Hamiltonian can couple the Bryan cat with the different symmetry eigenvalues. So with the way fewer terms in the reduced Hamiltonian that really couple the Bryan cat with different symmetry eigenvalues, the measurement cost has been significantly reduced as well. And the symmetry that we choose is called orbital seniority. So somehow the animation doesn't work here. So it is actually a set of singly occupied molecular orbitals, and that can be used to, they are also coupled to give you the overall spin of the state. So we are interested in a singlet state, for instance. And this orbital seniority has been used to, it has been shown to systematically approach the Fuzzy result, the exact result, by slowly, systematically increasing the seniority number. So with all this, we are using this scheme, and then in combination with the quantum subspace eigen expansion, we came up with this scheme called quantum seniority-based subspace expansion, or in short, QSENS. The QSENS functions are prepared by applying two unitary operators back-to-back onto the Hartree-Fock reference, so V and W. And then the V operators, when it acts on the Hartree-Fock reference, it creates configuration state functions with a set of single occupied orbitals, and well-coupled. The spins of the unpaired electrons are coupled to overall spin. So this is actually seniority, the animation that didn't work in the previous page. So here we have two unpaired electrons, two single occupied orbitals, seniority is 2, and then here seniority is 4. And then all the artificial symmetry has been delivered by the V operator. And next, we apply the W operators onto the states generated by the V operator. The W operators, for instance, excite this pair of electrons from the doublet occupied orbitals to the empty orbitals. And similarly, from here, doublet occupied orbitals to empty orbitals, and the products of the simultaneous excitation of the two. So W conserved the symmetry. It doesn't create any single occupied orbitals anymore, okay? But it actually enhance the level of correlation by this pair conserved excitation. So overall, this W operator, it comes with a product of elementary unitary operators, which comes from excitation and de-excitation of the doubly occupied orbitals and empty orbitals with the excitation amplitude theta here. Eventually, it only counts on spatial orbitals I and A. So we only need to reserve cubics for spatial orbitals instead of spin orbitals. And that means a twofold reduction in complexity of gate and in measurement cost as well. So that saves a lot. The ground state energy and ground state wave functions, they are functions of the excitation amplitudes of the orbital pairs that are included in the W operators. They give us some space for variational optimization. We can optimize the amplitudes to reach the ground state, for instance. There are two versions of QSENS. We call it the variational optimization or VO version. In these versions, we have a smaller number of states, and then the complexity of the correlation is translated more to the unitary transformation of each of the basis set. So we have a longer circuit in this VO version for each of the bases, and we have to optimize the circuit. Otherwise, the ground state would not be ideal. And the other version, we call it perturbation version or PT version. We translate the complexity of the correlation function into a larger dimension. There are more basis functions now, but each function features a shorter circuit, and ideally with analytically predetermined parameters, for instance, from Laplace perturbation theory. So we don't need to optimize the W operator and the excitation amplitude anymore. Overall, the comparison of VO and PT can be framed into a broader spectrum of trading off of the classical versus quantum resources. In classical, for instance, we have there's no circuit at all, but the dimension is huge. In VQE, we have a smallest dimension of 1, but then the complexity the circuit is very complex. But for VO and PT, they are at the middle, but one is closer to VQE, the other is closer to PT, closer to classical CI. And then we use the nitrogen and water as the two testing case molecules to demonstrate the robustness of our methods. And we focus on the bond stretching because then we can examine the methods, how they work for different regions of correlation. In the bonding limit, we have weak correlation of electrons, but in the dissociation limit, we have strong correlation of the electrons. And the STO3G basis is used, and then we have our Python code to run the proof of concept calculation. And then here we show the result for water and N2, and for the whole dissociation process, we have very good error. So the error is way smaller than the chemical accuracy from FOCI, and similar for water as well. So both methods work, both versions of QSENS works. And also for both the weak and strong correlation region. And the size consistency is demonstrated because we can dissociate to the appropriate atomic limits. So the energy of the complex is equal to the summation of the energy of individual components. And here we quantify the resource consumptions. So we compare the number of states that are involved in VO and PT. It's about 3 times here, more for PT, and about 8 times, 7 times here for PT. But it comes with the shorter circuits and a smaller number counts of CNOT gates. So overall, it's the balance between them, and here we compare them. And then compared to classical CI, the reduction in dimension is obvious. And in terms of measurement cost, we have a metric here. That's the millions of numbers of shots to reach the millihartree accuracy of the ground state energy. So we compare VO, PT versus VQE for the 2 systems for 3 representative structure. Now, one obvious observation is the structure dependence. For instance, we have 4 orders of magnitude difference here and 4 orders of magnitude difference there. But VQE, it changed, but not as much. So we have structure dependence on the cost. This is an upper side because actually the sampling is based on needs. So for those structure that the correlation is weak, and then we don't need to spend lots of samplings on the configuration at all. So we are not wasting resources by using Q-sense. And when we have a broader comparison of VO and PT, we see that PT usually works better, but PT can work a little bit not as nicely. But this should be understood that PT, even for here, is a high cost but 1 shot only. And VO is many shots of lower cost. So overall, PT is still good. And then overall, when we compare VQE and Q-sense, we have about 10-fold reduction in measurement time. So that's a significant improvement. So overall, this is our paper. We put it on arXiv already, and the QR code and the ID are here. And then we have a balance between the classical resources and quantum resources in this Q-sense formalism. We significantly reduce the measurement cost by artificial symmetry, which can be understood as the quantum version of Slater-Condon rule. And also, because we have more than 1 eigenstate, we can translate the method to static excited states and also to non-Hermitian Hamiltonian. So in the end, I need to thank the collaborator, and then Smig, the graduating PhD focusing on measurement, and then Praveen, who is sitting in the audience, and then he's focusing on designing gates, and Rick in undergrad, and then he's focusing on applying the method to non-Hermitian Hamiltonian, and Arthur certainly for brewing the idea, and then all the funding agents, and then thank you for your attention.
Thank you very much, Taoi. So it's now time for a little break. We will reconvene at 11 sharp. Thank you. Alors, c'est le temps de reprendre place. Now time to sit back again. We will start shortly. Yeah. So our next presenter, she's from Norquantic. Roya Radgoar is a quantum application scientist, and she will talk about Norquantic's work, quashing logical errors with multimode quantum error correction. So, Roya, floor is yours.
Hi everyone, good morning. It's a pleasure to be here. Thank you. Thanks to the organizers for the invitation to speak today, and thank you to all participants for being here. Today I'll be giving a presentation on the recent work done in Norquantic, quashing logical error with multimode quantum error correction. So in Norquantic, our vision is to build hardware-efficient quantum error correction. Our approach is to alleviate the overhead associated with error correction. It outperforms the it performs error correction directly on a single qubit and not using so many qubits. So it eliminating any physical overhead. These error-corrected qubits result in a low error rate for operations on the logical qubits, which is essential for practical applications. Our system is scalable and support fast clock rates, enabling logical operations at megahertz speed within a single connected superconducting architecture. To advance the technology toward utility scale, we developed multiple devices. We started by a single mode unit employing autonomous quantum error correction, pushes the limits of the state of art of quantum error correction. We then built multi-mode units that leverages multiple bosonic modes to encode logical qubits, increasing robustness against auxiliary induced errors. We developed a multi-unit architecture consisting of 16 modes, where the current design is extensible in a square array. With control performance, multi-mode unit, and multi-unit architecture, we are combining our efforts to build a fault-tolerant quantum processing unit with autonomous quantum error correction. To explain quantum error correction, I begin by introducing the single mode GKP qubit, followed by an overview of quantum error correction and single qubit gate implementation. Each Q mode behaves like a harmonic oscillator with infinitely many energy levels. Bosonic codes exploit intrinsic structure of quantum harmonic oscillator to achieve precise control over individual energy levels while reducing physical redundancy. We can generate cat state, which is a superposition of two coherent states. And they are robust against bit flip error because the noise should be very high to destroy the coherence between two distinct parts of the states, but they are susceptible to phase flip. This gives a strongly biased noise channel. We can also generate GKP state, which has periodic sharp peak along position and momentum. They are robust against small shifts in both quadrature, so they can correct small displacement errors. The bias for GKP state is less strong compared to the cat state. A single qubit is composed of a high-quality oscillator, a nonlinear auxiliary, and a readout resonator. Okay, grid codes are a class of bosonic codes that encode discrete variable logical information in translationally invariant lattices in phase space. This plot shows the Wigner function of the GKP state. The logical information is encoded in the relative positions of grid points and not in a single point or a specific quadrature of the phasor space. The grid structure can be measured by stabilizers without measuring the logical information. It allows for robust error correction without losing the encoded quantum information. The figure at the bottom shows the position wave function for logical 0 state, blue curve, and for logical 1 state, the red curve. That's for GKP state. And the figure on the right side, it compares the channel fidelity of several single mode bosonic codes like cat state, binomial, numerically optimized, GKP square, and GKP. It's applied as a function of the loss rate, since the GKP outperforms other bosonic codes in mitigating channel errors. North Quantic decided to use GKP state because of its superior performance. Last year, North Quantic improved error correction scheme using autonomous quantum error correction. And this approach, the quantum error correction, can be performed by SBS, small, big, small, big, BSB, big, small, big, and ST sharp and trim protocols. The protocol starts with the initialization of GKP logical states with a depth in a circuit where each layer consists of an auxiliary rotation and a conditional displacement. And the conditional displacement is a kind of operation that occurs between auxiliary and storage mode. It's followed by SPS protocol, and the final state is measured using tomography. The circuit shown below illustrates the conditional displacement, which will be discussed in detail later. The autonomous error correction exceeded the break-even point by a factor of 2.2 and provided a 24% gain over the GKP state without quantum error correction. The autonomous quantum error correction can be also improved by optimization. The top plot shows the logical fidelity without quantum error correction, with default quantum error correction, and with optimized SPS protocols. The bottom plot shows the logical lifetime obtained experimentally and numerically. The horizontal dashed line corresponds to the logical lifetime without quantum error correction. It proves that the autonomous quantum error correction extends logical qubit lifetime. Okay, having conditional displacement and auxiliary rotation, we are able to build a universal set of single gate on GKP logical state. Average gate for a full single qubit gate set, as shown in this plot. The average fidelity of single qubit gate is 0.85. Now we are ready to describe two-mode tesseract code. We will start with state preparation. I first explained single mode square grid code, then extended to two-mode tesseract grid code. The left figure shows a single mode square grid code. The phasor space is two-dimensional plane. The stabilizers correspond to translations in phasor space by square root of 2 in both position and momentum. The stabilizer matrix is generated from the stabilizer lattice vectors placed row-wise. To detect errors, we need to have the logical displacement operators that preserve the code space while changing the logical state. They are generated by the dual matrix, whose generator matrix is S matrix, is S star matrix. In this context, the distance is linked to the length of the smallest translational error that cannot be corrected. In this case, the distance is 1. A two-mode tesseract grid code is the four-dimensional generalization of single-mode grid code. We start by two independent single mode and then apply mixing transformation and rescaling factor and obtain S and S star matrices. The distance is the fourth root of 2, as can be seen here. For two-mode tesseract code, we have larger distance compared to the single mode. To enable entangling operations between bosonic mode, we use the echoed conditional displacement. The generalization from single mode to multi-mode ECD is straightforward. A single mode ECD composed of conditional displacement, auxiliary pi pulse, and free time evolution under dispersive interaction, and an auxiliary virtual Z-gate. The last displacement pulse is scaled by a factor of zeta to correct for displacement errors. The virtual Z-gate corrects for a finite geometric gate accumulated during the ECD. The right circuit shows its extension to multi-mode ECD, in which multiple displacement are used to achieve a conditional displacement of amplitude beta. This slide shows how we prepare and characterize the tesseract code. The circuit depth for the state preparation protocol with multimode ECD is between 12 to 15. Finite energy parameter delta is 0.45, which correspond to around 2 photon per mode. The circuit is composed of the state preparation protocol for the tesseract code, where we use two-mode ECD instead of single-mode ECD. This figure shows ideal joint characteristic functions of a two-mode tesseract code for different logical states. The plots in the first row provide a complete characterization of the logical state. The second row probes the single mode stabilizers, where the horizontal axis displaces mode 1 and the vertical axis displaces mode 2. The third row probes the two-mode stabilizers, where two modes are displaced together in correlated directions. Here we presented experimental results for the same parameters mentioned in the previous slide. They are very close to the ideal one. In this part, we discuss autonomous quantum error correction for two-mode tesseract code. This slide shows how quantum error correction can be realized through engineered dissipation. The main idea is to transfer excitations or errors from the logical GKP oscillator to an auxiliary system, such as qubit, and then reset the auxiliary to remove those excitations from the system. And this way, the system continuously cools itself toward the logical subspace, so corrections happens autonomously without any explicit measurement or feedback. Mathematically, this process is described by the Hamiltonian written here, where delta is the parameter related to energy. The unitary can be rewritten as SPS protocol, which is a sequence of auxiliary rotations and ACDs. The SPS protocol for autonomous quantum error correction is able to correct errors arising from dephasing, photon loss, small displacement, but it cannot correct the errors coming from the large displacement. We can easily extend the SPS protocol from the single mode to multi-mode code. The first circuit is one round of single mode SPS protocol for single mode grid code. where we have one storage, the circuit composed of auxiliary rotations and single mode ECD, followed by qubit reset. In the second circuit, there are two storage, storage 1 and storage 2, and single mode ECD is replaced by two mode ECDs. North Quantic is the first company in the world to perform quantum error correction on two-mode tesseract code. The circuit for state preparation and measurement is shown here. It's composed of state preparation with n layers of two-mode ECDs and auxiliary rotation, followed by tomography. In order to apply quantum error correction, we add SPS protocol to the previous circuit. This circuit shows complete protocol used to prepare, correct, and measure logical states. Each quantum error correction round takes 2.7 microseconds. These two plots compare logical fidelity as a function of the number of quantum error correction rounds in the absence of mid-circuit measurement that we will discuss later. The left plot is for single mode square grid code, and the right plot is for two mode tesseract code. It indicates that a logical error per round as 2.1% for two mode tesseract code. In this part, we'll discuss quantum error correction with confidence information. Before moving to the multimode quantum error correction, it's important to understand how errors can arise within the single mode SPS protocol. This slide illustrates the key error during SPS round for single mode grid code. In the SPS protocol, a large displacement occurs in the middle, shown by this arrow. And as this displacement takes place, the system traces a trajectory in phase space that implements a stabilizer operation. If the auxiliary decays halfway through that trajectory, the displacement is interrupted. And instead of completing the full stabilizer, the system ends up somewhere between two lattice points in phase space, and because the stabilizers in the single mode GQP code are parallel to the logical Pauli operators, this incomplete displacement corresponds exactly to a logical error. You can see this represented in the phase space diagram at the bottom left. That's why we refer it to an undetectable error. It's not detected by the stabilizer measurement because it lies exactly within the logical subspace. This limitation motivates moving to multi-mode version, where we can design stabilizers that are no longer parallel to logical axis, enabling to suppress this type of undetectable error. Now that we've seen how auxiliary decay during the big displacement can lead to undetectable logical errors in the single mode code, let's look at how tesseract grid code can fix it. The circuit at the top shows one quantum error correction round. For tesseract code, the large displacement shown by arrow still plays the role of a stabilizer operation. The crucial difference compared to the single mode case is that the stabilizers in this multi-mode code are not parallel to the logical Pauli operators. You can see these in the vector diagram on the right. The stabilizer directions S1, S2, S3, and S4 are rotated relative to the logical axis X and Z. Now, when the auxiliary decays during the big displacement, it no longer produces a displacement that lies entirely within the logical subspace. And instead, the resulting state is pushed out of the code space. This means that the error becomes detectable. This slide compares how a specific error behaves in single mode versus two mode GKP codes. And the single mode GKP, the auxiliary decay error stays within the code space, acting like a logical operation and remaining undetectable. In contrast, the Tesseract code, in the Tesseract code, the same error moves the state outside of the code space, so it's detected and corrected. This is why two-mode codes have fewer silent errors compared to the single-mode GKP. We can perform mid-circuit measurements on the auxiliary qubit to obtain real-time confidence information during quantum error correction. If the measurement outcome is 0, it indicates either no error or a silent error. An outcome of 1 signals either correctable error detected or uncorrectable error detected. Since the Tesseract two-mode GKP code has fewer silent errors than the single-mode GKP code, the resulting confidence information is generally higher. This plot is an example of mid-circuit measurement outcomes for 16 quantum error correction round. Green color indicates ground state, and yellow color indicates excited states. And the full erasure limit, a valid shot indicated in blue, as one where all measurement outcomes correspond to the auxiliary ground state. The second plot displays survival probability as a function of the number of quantum error correction rounds. The line indicates an exponential decay. The rejection probability is obtained as 12.6%. The figure in the bottom shows the increase of logical error as a function of the number of quantum error correction rounds without erasure and with full erasure. The full line is the exponential fit, proving the logical error per round of 3.5% for the case of no erasure. So in case of no erasure, the logical error per round increases from 2.1 to 3.5%. In case of full erasure, we keep only shots in which no flag has been raised. We see logical error decreases for up to 32 rounds, and future directions could be soft post-selection strategies to trade off logical decay and rejection rate and improve state preparation to remove transient. In order to use bosonic codes to suppress logical errors, there are two approaches: adding more photons per mode or adding more modes per logical qubit. To the best of our knowledge, this is the first ever experimental demonstration of Tesseract multi-mode grid code showing improvements over single-mode GKP qubit. The quantum error correction is performed on part with single-mode grid code, and mid-circuit measurement is used to remove flagged outcomes. The experimental results show that no logical decay detected for 32 quantum error correction rounds. However, North Quantic primary objective is to build fault-tolerant quantum computers. The architecture of our hardware enables for implementation of a new version of quantum algorithms known as continuous variable, discrete variable algorithms. The continuous variables are encoded in Q modes, while discrete variables are encoded in the trans mode or in the qubit. NQ's and ESA is a phase space ESA, including conditional displacement, rotation, and beam splitters. And it provides universal hybrid control. It can be useful for simulating systems with fermions, bosons, and also spins. We have external collaborations in the application team. In the AlgoLab collaboration, the goal is to develop algorithms tailored to North quantic hardware. We performed analytical calculations for Trotter-Suzuki decomposition of quantum gates, simulated the gates on the North quantic emulator, and demonstrated the limitations and the advantages of the method. With OTI, we are developing quantum algorithms to simulate vibronic spectra of OLED industry. For phosphorant complexes, the full molecule has 55 atoms, correspond to 159 vibrational mode. The classical treatment becomes costly in this case. However, the bosonic hardware enables direct encoding of vibrational modes and significantly reducing classical preprocessing and resource overhead. So we can reach quantum advantage in this aspect. And thank you so much.
Thanks a lot, Roya. We have time for one or two questions, if there's any from the audience. I don't see no questions, so we'll move on to our next presenter. Simon Verret is a quantum... Oh, we have a question. So, Roya, you have a question at the end back there. So for the people online, the question is about the size of the device and how it will be scalable.
If you are asking for multi-mode bosonic code, multi-mode is just one cavity, and different modes are there. Mm-hmm. I'm not sure about this question. Maybe you can ask people in the design team. Yeah, okay, sorry.
Okay, so our next presenter, Simon Verret, is a quantum software developer at the AlgoLab here at Institut Quantique. He's going to talk about calculate Green's function to reduce the error on energy expectation value. Well, Simon, all yours.
1, 2, 1, 2. Can you hear me? Let me get a little bit more volume from this analog control here. Okay, this works. No, wait. Yes. Oh, right. Okay, so I'm talking to you. Yeah, I'm a developer at AlgoLab. This is an interesting work, in fact, because it was entirely made at AlgoLab. So it was pioneered and developed first by Alexandre Follet, who is in the room right now at the end here. And now we are working with Olivier Naman, who is also a programmer at AlgoLab, and interns that joined us. Jérôme was working at the early stages of the method with Alexandre. But yeah, a lot of people got into that work. And my main takeaway, and you can stop listening after that slide, so you should listen to this one at least. My main takeaway is we developed a new algorithm that improves energy estimation given an existing ground state circuit by computing the Green's function for that system. So here you see a figure that I will show many times in many various forms, but the horizontal lines on that plot are energy estimated as expectation values of the Hamiltonian. So you can see that the simulation for that particular ground state circuit was a lot off from the true ground state, and that if you run that on the actual quantum computer, you get even more away from the true ground state. Whereas if you compute the Green's function with our algorithm, which proceeds in a bunch of iterations. The simulation and the hardware computation works, they work quite well to get you close to the true ground state. And the way this works is by using a clever set of observables. So it's a little bit a sample-based approach in the sense that we build many observables. We use one circuit and we just extract as much as we can from that circuit. So I'll tell you why it's interesting to be able to do that, talking a little bit about quantum chemistry. We'll look at the new algorithm and a bunch of Green's functions. I'll look into more hardware experiments to convince you that it's interesting. And then we'll look at computational costs, scaling, and future work. About quantum chemistry, why would you use a quantum computer in the first place? Well, the way I understand it is the hello world of quantum computing, quantum chemistry, is the dissociation between two hydrogen molecules. If you move those molecules away and compute the ground state at every distance, you get a dissociation curve. The state-of-the-art quantum computing on quantum chemistry is also doing that right now. So you can see the red points here are IBM's latest attempt at getting the dissociation curve for nitrogen on 58 qubits. And the main interest in this is that if we can do that for two molecules, we could do that for more. We could do that in the presence and absence of catalytic molecules or enzymes. And then we can find reaction pathways that are more efficient. And if you don't think this can change the world, in fact, it already has. In the early 1900s, we discovered a catalytic that was able to fix nitrogen, make fertilizers, and solve a global starvation. It saves us from global starvation. So I have good hope that doing the same thing, we might be able to fix carbon somehow and maybe even reverse the effects of climate change. So I think that's a very important question. All you need to do to be able to go in that direction at least is to compute the ground state, to get the ground state energy. Once we'll have fault-tolerant quantum computers, we might be able to do that with quantum phase estimation, but we have to do that faster than fault tolerance, ideally. A few years ago, quantum variational algorithms were proposed for this. You prepare a state with a bunch of parameters, and when the state doesn't get you the good energy, you just optimize those parameters until it gets you good energies, and this was a very promising idea. Unfortunately, experiments showed that it has barren plateaus, it gets into problems. This is linked to a concentration of measure in the Hilbert space. It is a really general, we won't get away from that. And then there is noise on the actual computers, so it doesn't work that well. Let me convince you that variational quantum eigensolver are difficult with a simple example, which is the Foresight open boundary condition Auburn model. I'll use that a lot in the rest of the presentation. So Foresights, if two electrons are at the same place, they don't like it, they want to go away, and they can move around. So it takes 8 qubits to simulate that system. 8 qubits in a huge variational circuit like this will get you very, very close to the exact ground state. In fact, you don't even see the black line here because it's exactly where it should be, and you get very good fidelity. So for that small system, we can do everything to the end. However, if you just try out variational eigensolver on that, sorry, Julien was an intern that took a long time to get us that circuit, so respect for that. Because if you do it naively, and that's my first attempt, so I did that for a few days, and the best I could do was this one here. And then I asked an intern to do a lot more of these, and I will show you 5 of them. So different circuits, this is a different kind of ansatz, gets you good fidelity for bad energy somehow. And yeah, you never, so it's more an art than a science at that point. It's hard to get the right ground states. Thank you, Thomas, for going through that pain. Now we have a bunch of them that we can study. And yeah, I will come back with that figure for the rest of the talk, and those will be my 5 circuits. So yeah, the new algorithm. I will flash some math. The important thing is we want the Green's function, and this is the definition, but we will use the Green's function in frequency space as a continued fraction. So what we want are these coefficients, those alphas and betas. These are the output of the algorithm. The way it works is we start from the Hamiltonian in an initial operator, and we generate a bunch of operators that gives us, by estimating expectation values, those parameters that we cared about. The initial operator is a creation operator because we want the Green's function. And and thanks a lot to Alexandre and Jérôme who have developed and test this thing. It took them a long time, so they should get credit for that. Here is the method at play. So you see the iterations making the greens function evolve, and very quickly, so let me do that again. Very quickly, you can see that we get close to the actual greens function. It's just that a bunch of energy levels and poles are moving around. This is the spectral weight. It is the imaginary part of the greens function. That's all you need to care about. And I was doing this algorithm now with that starting circuit, which is perfect. So how does thing goes when you don't have a perfect circuit? If you don't have a perfect circuit, at first, it looks very similar, almost indistinguishable. You get very close to the true, but the end result is a little bit less good. This one is very bad. In fact, it's completely asymmetric. This one gets you very close to the right result, but those peaks are a little bit off. And you can see that it's not clear what in the ground state circuit gave us good or bad results. So we have to be aware of that. Now, a way to objectively measure that distance to the actual solution is to use the Wasserstein's distance. So it's an intuitive, in an intuitive picture, it just computes how much you have to move at a given probability distribution to the other one. We do that by computing the cumulative distribution and taking the area under the curve. If I do that I compute that distance for a bunch of iterations to the true solution, you see that starting from the exact ground state, it would take us some time to get to this. So this is the ideal that we could get. The blue ground state follows that perfectly up to 12 iterations and then gets a little bit away. The yellow ground state is a little bit worse. The green one is completely bad. The red one, the red one is a little bit better than the yellow. In fact, we could saw that in the greens function, and the purple is kind of in between. So we have a spectrum here of good and bad solutions that I will use to demonstrate the rest. So yeah, I told you at the beginning, my main takeaway is not to compute the greens function, is to estimate the energy. So how do I do that now? So new algorithm for the energy. The key is to use what is called the Galitsky-Migdal formula, which is an integral on the complex plane for that greens function that we just computed. A subtlety in this is that you need to get access to the off-diagonal component of the greens function. I will only say that with Alexandre's method, it is easy to do that. It is a little bit more efficient computationally to get those off-diagonal elements, and that's why the method is interesting, especially for the energy. So in the exact case, that black line here gets you to the energy very, very quickly. In fact, you can see there's a little bit of oscillation, but you are in the right ballpark right from the start. With the blue ground state, things go really well. With the yellow ground state, and I put that horizontal line here to guide you through what the expectation of the Hamiltonian will give, the yellow ground state gets you close as well. And then it starts getting interesting, because even if you have a bad energy for the ground state circuit, you kind of converge at the right place. It moves around a little bit, but you stay in the right ballpark. And this is true for very bad ground state, as you can see here and here. So it seems when you put all of this together, that even if you have bad estimation for the circuit energy, you can get good estimation with the greens function. We did that, in fact, thanks to Thomas. We did that, in fact, for so many starting VQEs that we could say that it's always a good idea to at least try the method using the circuit, because most of the time you can get close to the real energy. You need some fidelity with the true ground state, because otherwise you can get anything, but that was expected. But yeah, it's an interesting the direction. So what happens on hardware? Because when things goes well in simulation, typically everything goes bad once you use the real computer. So the real computer is the full line that you see here. So with a very good ground state, that was a very deep circuit, remember, we get on par with what you would get using the estimation of the Hamiltonian. And this is probably bad because it's a deep circuit. Things get a little bit better with the yellow one, and it starts getting really interesting with the green one, the red one that you saw at the beginning, and even the purple one. So my message here is that the method seems to be robust to the hardware noise for some reason. And this takes me to what we could do in the future is asking that question, why is that the case? Regarding computational cost and scaling, this is where the method is not free. What happens is that, remember I told you, we start from the Hamiltonian and we build a bunch of operators. Each of these operators has to be decomposed in a sum of polystrings, and the number of these p's grow very fast, up to the limits of as many p's as you could get. So it doesn't grow exactly exponentially. You can see that it's a little bit sub-exponential, so that's promising. The good news, however, is that remember that we were converging so fast that the method might be useful in the regime where you don't have to compute that many of the polystrings. You can probably do 5, 10 iterations in the case of the Hubbard model and get away with it. Another good news is that if you look at the coefficients of these terms, a lot of these terms are very, very low. And you can get away with probably, and we'll have to test this, but you can probably get away with truncating a lot of that collection of p's and still having good results. So as future works, we are looking into this, like what's the minimal operator subspace that we need to deal with? Can we do that algorithm with classical shadows, so you won't have to do all of these measurements? Maybe you can just like extract the information from a few of them and use that to do the rest of the algorithm. And we want to look at the noise robustness. Why is it so good even with noise? And of course, we want to scale up to bigger system because that was only an 8-qubit experiment. So people are working on that right now. So Thomas is looking at the poly operator subspace. Olivier is preparing a paper on the classical shadow case. And Felix is looking at the noise robustness properties. And that's it. As a conclusion, let me just put back my takeaway. We have a new algorithm purely made at AlgoLab, so we're really proud of that, that improves energy estimation of existing ground state circuit using the Green's function, which we know and love in Sherbrooke. So we do that by using a clever observable set, and we'll look deeper into this in the next 2 years. So thank you very much for your attention.
Thanks a lot, Simon. We have time for one question if there's one from the audience.
So as you saw,
Can you repeat the question?
The question is, how does it compare to the exact, the same classical algorithm? So the key, let me bring back this one. Yes, this is a 4-side Hubbard model, which we can solve exactly. So it is a test case, right? Here. So the interest lies in that thing. If you would do this classically, or if you do the classical Langshos algorithm classically, you need to express the Hamiltonian in a full Hilbert space basis to perform those expectation values. So anytime you do that on a quantum computer, it might be a little bit better just scaling, because you get the exponential space in the computer instead of in the classical computer. So the main cost comes from handling all of the classical operators that you build using that recurrence relation. Because once you have those, you just have to measure them, and the Hilbert space is in the quantum computer. But the number of those operators grows really fast, so that's the difficulty. But at scale, like for large quantum system, it would be exponentially better than the same classical algorithm on a classical computer. The same algorithm on a classical computer.
So save your other questions for lunchtime. We will now move to the panel of the morning. So if the panelists want to come on stage. So let me introduce you to our panelists of the morning. Please welcome Camille Brun-Jolicoeur. She's a Quantum Partnerships Manager at IBM. Also, Michel Lampa, head of sales and operations at Pascal, based in Boston, if I'm not mistaken. Thank you for having made the trip to here this morning. And finally, Claude Rachbacher, senior experimental quantum physicist at Equal One. So thank you all for being here. So the title of the panel this morning is Applied Quantum Computing on the Path to Fault Tolerance. And this is why we wanted to have representatives from many companies that you, of course, have heard of, either, well, today or on other circumstances as well. Well, thank you for being here. Well, before we jump into the hard questions here, can you please, well, introduce yourselves briefly and, well, maybe have a line about your background as well. So, Camille?
Oh, I go first. Nice.
Yep.
It's very intimidating having everyone look from above now, but I'll be fine. So I'm Camille. I'm pretty new at IBM. Started 3 months ago. I come from a consulting background, so I'm sorry about that. Scholars here, but I was working in consulting for the past 10 years, a little bit more toward implementing AI in the big private industries, mainly banking and public sector with ministries and stuff. I did my studies at Polytechnique, so I'm an engineer by training, and then I did my master in data engineering just across the street, so kind of local. I don't get that lost in the obscure tunnels here. So yeah.
Michel, yeah.
Hi. So I totally got lost. I am not from here, so it was kind of difficult for me. I'm totally wearing this hat from the Canadian Consul General's office, I think in Chicago, that actually created this. And so you'll see that Quantum likes the cold or loves the cold, and you'll see the little maple leaf, which is great. Go Canada. I'm Michelle. I am the head of sales and operations for North America, Pascal USA. This is actually, we just launched our US subsidiary in Chicago, but also we have a secondary QPU manufacturing site right here in Sherbrooke, so that's really exciting. This is actually my third US subsidiary I had launched for quantum startups based out of Europe. This one is Pascal, so we're full stack neutral atom quantum computing company. Before that, I was at a UK-based quantum error correction company, Riverlane. So exposure to the over 9 different qubit modalities and where we actually were for quantum error correction. And then before that, I was at M-squared lasers, so lasers for various different quantum applications beyond just quantum computing, so quantum sensing like quantum accelerometers, gravimeters, as well as quantum optical clocks. But I did not have a quantum background, so getting here was not easy. I started off in international business, and then I put a hold on my career to learn full stack web development. So somehow object-oriented programming helped me understand quantum electrodynamics and quantum mechanical theories. And it's been really fun in having those conversations and translating for everyone. So that's me in a nutshell.
Thank you. And Claude?
And I'm Claude Horbacher, and I'm a physicist. I have a degree in material science and engineering and electrical engineering, and then I did my PhD actually here in Sherbrooke, working in the experimental measurement of spin qubit devices, which is what I still do at Equal One, which is an Irish startup which actually opened an office here in Sherbrooke 2 years ago. And we build a full stack quantum computer based on silicon spin qubit using the same manufacturing capability as the microelectronic industry.
Thank you all. Well, can you now talk about, well, the road to quantum error correction? Maybe describe some projects that you have in mind or milestones that are coming next. If, of course, error correction applies, of course, in the case of Pascal, it may not be exactly this, but if you want to maybe also talk about this difference in approach between quantum analog and quantum gate-based, for example. So, Michel, yeah, we can start with you.
Okay, got it. Yes, so we were actually co-founded in 2019, which is pretty cool. And people think like, wow, that's fairly recent. But because we were actually co-founded by Alain Aspect, the Nobel Prize winner for quantum entanglement, our technology has been in the works for over 30 years. And it's been really great because we were founded technically in 2019. That was the moment that we decided, all right, we have an MVP that exists in the lab. How do we actually make it more accessible? How do we get people to actually want to use our stuff? Let's actually create a product-led company around this product, and it just so happened to be analog. And 2024 was actually a big year for us because it was the first time we actually started to not only just manufacture our products, but delivered and integrated our devices to high-performance computing centers, as well as also become enterprise grade in a way, in which we were able to actually also sell our devices to Aramco, so the largest oil and gas company in the world. So you're starting to see major companies really want quantum computing. Now, what does that actually mean? We know that analog has major value, so we can do kind of polynomial optimization problems, which I believe is kind of difficult for some of the more digital aspects for certain other companies that are in the space as well. And so we've actually developed over 35 major collaborations with over 35 partners, over 40 use cases in which quantum has provided major value for them. Now, for everyone who's in the science world, quantum value means, exponentially better, right? But for companies and for them to get to that point where they need to adopt a quantum hybrid workflow with classical today, polynomial is enough for them. And understanding what is needed for what that workflow needs to look like is very important. So to give you an idea, most of the companies that we want to sell to one day don't have a quantum team. And yet everything we just talked about and what everyone just talked about is about like Hamiltonians, Pauli twirling, and Pauli operators. How do we actually translate that to actual value? That's something that we're working on. And so we have our devices that we've already sold and integrated at 100 qubits. 200 qubits is what we're delivering today. R&D is 1,000 qubits. And then by the end of the decade, we plan on having 200 logical qubits, so having that digital approach. However, though we have these 40 plus use cases, at least in analog today, what we want to see in digital, we haven't yet explored. We just launched our first logical qubit that has circuit depth, so it is going to be scalable as opposed to just getting as many qubits or even how many logical qubits as possible. We want to make sure that they're useful.
Out of curiosity, the machine you're building right here in Sherbrooke, when would it be available, you know?
It's available now.
It is? Okay, so it runs.
Yeah. And actually, I forgot to also mention, so Philip Babin is also here. He's the CEO of Eponix. We actually made a strategic acquisition of our roadmap for fault-tolerant quantum computing. And Eponix is actually our strategic acquisition that we've just made. They focus on photonic integrated circuits, and we're going to be using that technology to integrate it into our existing technology, where we can move our qubits around towards fault-tolerant quantum computing. So the work that we're doing here is going to be very incredibly useful and important for our overall roadmap.
Thanks. Claude, on your side.
Yeah, so maybe one flagship project that actually was recently announced Monday is that we're going to deliver a machine to ESA, so the European Space Agency, to explore with them use cases, especially for Earth observation or to solve some optimization problem. And I would say as a hardware company, the road to fault tolerance is making a machine available. So actually building a quantum computer and making it available for people to explore use cases. And we're working towards that both internally and throughout, hence collaboration with ESA, but also we're really open to collaboration with theorists and people to help us explore what we can do with the machine and the range of possibility that is available there. So it's currently, spin qubits are fairly more recent than other technology. I think the first demonstration of experimental 2-qubit gate was in 2018, but because of silicon industry, we really hope, and I mean, it's demonstrating right now that we are scaling up quite fast also because we are building up on so much knowledge, both theoretical and practical in the industry. But yeah, I think the main work is now to explore some actual quantum error correction code with this machine that we're building, and to explore some use cases and discover applications that are really relevant for the hardware that we're building.
And out of curiosity, on the chips, is it a 2D spacing for the qubits?
The first 6-qubit chip that we delivered is a 1D array. Okay. And then the current machine that we have is upgradable to 17 qubits. And this will have some first demonstration of quantum error correction in there.
Okay, and what I get is that a bit like Pascal does, the idea is to sell the systems to the actual customers, and for the customers to have the quantum computers on site.
Exactly. So it's fully integrable into HPC system, meaning that it doesn't require any additional infrastructure to install. So it's basically a server rack with a tiny fridge inside. And it encapsulates all the control electronics. And the good thing with silicon is that in the future we are working on integrating the electronics at cold temperature, meaning that we will be able to reduce the size of the system, but also to improve the speed of decoders of quantum error correction, because all the control electronics and all the calculation will actually happen on the chip.
Okay, and what's tiny?
The current Bell 1 system is a 32U unit. So for people who don't know server dimensions, it's about as high as me, so 1.64 meters. I don't know what's that in inches. And it's deep as a server rack.
Okay.
Yeah.
Thanks.
And it doesn't require any chilling system. It's air cooled, so you could plug it into a regular outlet and it will run.
Good, fantastic, thanks. And Michel, what about IBM? You have a different approach to selling systems and also about error correction. So,
Camille. Sorry, it's fine. So it's my second name, so it's okay. So actually, for us, it's less tiny. We've been, for those who follow either Jay or IBM Quantum, yesterday we announced the launch of the Nighthawk chip with 120 qubit and with 42 more couplers that the current Heron has right now. So we're pretty excited about this milestone being achieved.
And this is 4 nearest neighbors on the chip, right?
I'm sorry?
The Nighthawk, every qubit has 4 nearest neighbors or connected to 4 neighbors?
Exactly. It would be, however, it will only be will be for deployment in QS2 only. And so that's pretty much what we've been excited about. It's like in our modular approach to our roadmap, we're just checking that milestone, and we also announced that we are ahead of schedule for the Loon processor as well yesterday. So that's the main flagship that we've been excited about right now.
And well, you talked about more connectivity. How is it related to error correction?
So for us, we're trying to put forward like all the building blocks. I'm not technical enough to be able to go into deep on that front, but it's to put every step forward toward that goal. It's also more aligned to run LDPC code for error correction as well.
Okay, so still thinking about error correction and moving into a fault tolerance quantum computing, where are we right now? So are we still in NISQ? When is starting error correction? So what's to come in the next years?
So for us, we're still in that movement. Even though everyone is very excited at IBM and elsewhere on like moving and just being active on the fault tolerance state, we cannot like wait for it to happen to actually move forward on the knowledge base and the research. We also deployed the Quantum Advantage Tracker right now, so we believe that innovation comes through community. And with community validated the claims of quantum advantage and error correction. So through that, we hope to be able to measure a little bit more where we're at in a more quantitative manner than a qualitative state.
Sorry, what was the question again? Quickly.
So we are moving towards fault tolerance and like quantum advantage. Right now we are still in NISQ. So where are we right now?
And thank you for that. It was more like I had something I was going to say and I completely forgot it for a split second. I need to buy time. But just,
Repeat again if you want.
no, it's perfect. So to clarify, we are not NISC. We are analog, and so in a way that that doesn't apply to us. And so a lot of the stuff that we've been doing is actually fairly accurate. I can't tell you, I'm not technical enough to tell you exactly just how accurate, but we are very, very accurate, at least on the analog side. And it is something that fault tolerant applications is something that we want to do. But we're just not there yet, as we talked about already. But again, our analog applications, at least for today, work today. For what we want to do for the fault tolerant side is something that, like I mentioned, for the logical qubits, we are building it so that is going to be scalable and usable immediately, and you don't have to worry about circuit depth and stuff. It's stuff that we're going to be adding into it. I know that that is a major priority for Pascal. So in the end, it's not just building as many qubits, but essentially making the quantum error correcting codes as scalable as possible and making sure that our architecture is enabled to handle that as we grow. So that is something that is a priority for us. But like I mentioned, there's stuff that we can do today that can provide value already.
And what about equal one?
Yeah, I think our main avenue is to think about scaling. I think to go to early fault tolerance, scaling is a more complicated thing that we think, because there's no clear demonstration now that someone has a very good architecture with very good qubits and error correction, and then can scale up to a bigger size quantum computer without losing those quantum error correction properties. And scaling decoders and scaling hardware is not as easy as we think. Especially the decoder part. So keeping a good quantum error correction property while scaling up the hardware is I think, the key thing that we're missing. And that's something that Equal One is working a lot, and we are trying to use silicon as much as possible to scale fast. But it's an hard part, and I think there's also a lot of work on the theory side to do, and on the experimental application of theory, meaning like magic state distillation, especially for gate-based quantum computing. I'm not a theorist, so I'm not going to say why that is important. I think there's people in the room who know that better than I, so go talk to them. But there's no clear demonstration yet of like a good hardware that's able to do magic state distillation properly to reach early fault tolerance. So I think there's a good amount of work to do on that as well.
Good, thanks. And my last question for you all will be, what's to watch next? What is this big next step for each of your systems that will come soon, or hopefully will come soon? Maybe we can go again with you.
I think the next iteration of our machine will be pretty cool. As an engineer myself, like co-integrated the electronics is something a lot of people have been working on, and we've seen the size of those fridges. And I think co-integration of electronics is not only for silicon spin qubits, it's for every hardware architecture. It's going to be needed just for the whole overhead of cables and of calculation that is needed. You cannot afford to have a football size amount of rack and computers enabled to run that. So for myself, from an engineering point of view, it's actually quite a challenge to bring all that heat, literally, into the device and still being able to operate a good QPU, and I think that's the way to scalability. Yep. So I think the next iteration of our machine will be very interesting. I think we're going to have some good news for Sherbrooke. We're actually now expanding as of a few weeks now. It's official, so we're going to bring a lot more people in the community. So we're now a very small antenna in Sherbrooke, and we're going to bring like 2 people now. We're going to bring 10 people into the next year. So I think also for locally, what's next is that we're going to be able to work way more with the community and integrate way more into the Canadian ecosystem. And for the whole company, it's going to be a doubling the size of the company everywhere in the world. So it's going to be pretty interesting years to come for Equal One.
Yeah, and your systems will operate at, well, pretty high temperatures, won't they?
Yes, no. So the Bell One machine is operating at 300 milli-K. That's the standard temperature of the machine. But we've actually published recently some data on the performance of our qubit up to 750 milli-K. So the goal is sort of to raise that temperature. And the good thing is that the only trouble there is not actually the fidelity of the qubit, it's the readout measurement that gets degraded. And the good thing is that there's some pretty easy scheme to integrate to sort of push that to higher temperature. So it's sort of work on both ways, we have a lot of integrated circuit engineers working very hard to limit the dissipation of heat into the from the classical electronics. And then we have a lot of physicists trying to bring the qubit as high as we can in temperature. So yeah, it's going to be exciting years to come.
Yeah, great, thanks. Camille?
Got it. Yeah, so for us, we've been, our roadmap is very public, so the next major milestone would be 2021 with Starlight coupling multiple QS2 together, with also a structure where we can have a data center at the same in the same space to put together all the HPC's power in a quantum system. What we want to see next as well is what's happening with the Canadian ecosystem. So as IBM is a big global company, but we have Canadian people here working for Canada, and we want to see the Canada market and all the partners and ecosystem and university work together to really put Canada on the map. So it's not about being competitive against each other internally here geographically. It's about us as a group being better than everyone else after that, comparing. So that's what we want to see next.
Good, thank you. And finally, Michelle.
So for us, I feel like there are two major things that are happening, right? BCG, maybe 10 years ago or close to 10 years ago, they said that there was going to be, when it came down to quantum computing, they were going to get to quantum computing faster with the adoption of certain applications than the hardware. But in actuality, what we're starting to see is that hardware has surprised everyone by actually accelerating and we're probably closer to fault-tolerant quantum computing than people realized even about a few years ago, and that is a huge thing. But how do we get to that point where people actually adopt the technology as well? And that workflow and that translation is the part that is actually missing. So I think there's going to be a lot of that happening in the next coming years. But for us personally at Pascal, again, the integrated control modules, for one, we are room temperature. We are equivalent to powering up 4 hair dryers. And we hope that doesn't change when we go from analog to digital. And so that's going to be a huge thing for us, especially by the end of the decade when we get to 200 logical qubits and what we can actually do with that, as well as build on our partnership with IBM as well so that we can hopefully get to that point where essentially an end user doesn't have to think about all the hardware requirements, what Hamiltonians they need in order to actually do the project and get the output they want. They can just push it through and it'll give them the output they want. So there's a lot of things going on for us, and those are, I would say, the top areas of interest: fault-tolerant quantum computing, getting the 200 logical qubits by the end of the decade, as well as making them more accessible, at least from Pascal's point of view.
Fantastic. Well, that was a quick glimpse at all your technologies. I'm sure there are many questions. Please use the lunch break for asking them. Well, to the panelists that we had, right now, also to other presenters that were there earlier this morning. So we will stop for lunch now. There's a few housekeeping things here on the page. We'll be back at 1:15 sharp. If you have indicated food allergies, please look for the lunch boxes with your name on it specifically. There is vegan and vegetarian options if you chose them, so please be aware of that. And all lunch boxes are recyclable, but cutlery is compostable. Please use the right bins. On that, please, thanks again to our panelists. And see you after lunch. Thank you. So it's time to come back to the auditorium. So I hope you had a great lunch, that you met with fantastic people. It is now time to start the afternoon. We still have a full schedule ahead of us that is very interesting, and you'll see that we will start that programming right now with a project that will be presented to you, which is great news for us. We got that news a few weeks ago, and we wanted to share with all of you what it was all about. So this next half hour will be a presentation of three people who worked on the project. Stefanos Courtis, who you met earlier, director of the Algo Lab, also physics professor here at Institut Quantique. Victor Drouin-Touchette, staff researcher also at Université de Sherbrooke, working with Stefanos in this instance, and Joseph Gibson, PhD student here in physics at Université de Sherbrooke. They will talk to you about this fantastic news. I won't spoil. I will let them talk to you about what the good news is. But the topic of it is Unlock Quantum AI by Taming Counting. So without further ado, please.
Thanks, Ghislain. I would like to thank the organizers for allowing us to present our work in this lovely symposium. I think part of the reason why we were invited is this news that Ghislain alluded to, which is this X Prize competition on quantum applications. And we were selected recently as one of the 20 semi-finalist teams. This is a global competition for the development of real-world quantum applications with real-world impact that will take place over the next 2-3 years. And we were selected amongst more than 130 different teams from a variety of very important research centers on quantum in the world. So this was a very, very good news. So the title on the program was something a bit more flashy than the title that I'm showing here. And so the plan is to explain to you what this work is about. And so, voilà, okay, merci. So the way we're going to do this is I wanted you to see the entire team. So I'll start to give you some motivation and overview about the work and put it in a more general context. And then you will hear from the other members, Victor and Joe, more specifically about what the proposal is and how it works. So let's start with a motivation. And specifically, you saw AI in the title, and AI is this very big thing that people talk about a lot from various perspectives. And so I wanted just to give you a bit of a background on why and how we are interested in AI in our group. So we are interested in computationally complex problems, and there's a variety of problems within AI. Some are more complex than others. So I made a very rough sketch here of what these problems are, starting from things that are generally broadly simpler, all the way to things that are a lot more complex. And one particular preoccupation that we have with these algorithms is safety, okay? And let me explain how computational hardness and safety may kind of be at odds with each other. So we are interested in building autonomous agents, right? Things that do, devices that do things by themselves without our own input. But at the same time, when these are deployed into critical industries where we care about the safety of data or humans or animals, we need to put in guardrails, right? So for example, I'm showing an example here. This is a self-driving car. On the bottom here, you see the different cameras. And you see the camera that is looking ahead is seeing a green light. And so the car has been programmed when it sees a green light, okay, it's time to go. But if you look at the bottom right there, even though the light is green, there is a fire hydrant coming. Okay, so clearly this is an unforeseen situation. In many cases it can be foreseen, where you can write if fire hydrant stop, right? So that's easy. But in general, incorporating more and more constraints such that we guarantee that an algorithm that learns by itself is safe means that necessarily we're increasing the computational complexity of training for this algorithm, for this agent, okay? And in fact, there's multiple curses there, dimensionality, rarity, history, etc., that we have to take into account. And so if we try to classify in a complexity theoretic sense these problems, they become really hard, really fast. And yeah, as I said, safety in many cases is equivalent to enforced constraints, but we know that constraint satisfaction itself as a general problem is a hard problem. And so because of this, safety many times is at odds with scalability. So our point of view is to start from this and say, okay, if we have a complex problem to solve, could we benefit from quantum computing in solving this problem and therefore enabling safe AI in the future? Okay, so that's the very broad perspective for this work. So there is a lot of work on quantum computers deployed to AI problems. A lot of it, and I would say most of it, is actually focused on what I call easier problems. Why is that? The reason is that in practice, most of our compute is dedicated to such quote-unquote easy problems. It's just that we have to do a lot of them, right? And so that's one way that people are investigating quantum computing in terms of AI. We, on the other hand, are mostly interested in the latter categories, meaning the problems that are harder, intrinsically harder. And we're trying to enable AI by devising schemes for attacking these problems in an efficient way, okay? So with this, I'm going to show you my very catchy slide for the problem that we are working on. I hope everybody's caffeinated. So we are going to talk about counting, okay? Counting in this context means that we have a set of objects, and we want to count how many of these objects satisfy certain properties, okay? And to formulate this problem in a broad sense, we can do this with a set of objects where the objects are the simplest possible objects. They are just Boolean variables, okay?
So I have a set of variables xi, I going from 1 to nx, and then I apply to these variables constraints. And the easiest way to apply constraints is just logical constraints. So one constraint, or clause as it's denoted there, could be, for example, I take the collective OR of these Boolean variables and I only accept the configurations that satisfy this clause or constraint. Okay, meaning when this constraint evaluates to true. So if I have one of these constraints, it's fine, it's easy. But if I have many of these constraints that need to be satisfied simultaneously, I obtain something like this formula, this graph of white and red nodes that you see there. And now the problem of determining whether there is an assignment of the Boolean variables that satisfies a formula like this becomes very hard. Okay? In fact, this problem of deciding whether there exists a satisfying assignment of such a formula or not is complete for the complexity class NP. Here we're going to talk about problems that are even more complicated, where we don't just ask, is there an assignment, or find an assignment that satisfies the formula. We ask, how many assignments satisfy this formula? And just by definition, this problem is a lot harder. How much harder? I'll show you in a bit. First, I will show you why we care about these problems. In fact, these counting problems are pretty widespread. So for example, in disordered systems, we have the partition function of spin models, for example, which boils down essentially to a counting problem. In engineering, in reliability engineering domain, we have, for example, network reliability, where we want to evaluate the reliability or the resilience of, say, a power grid subject to a probability of each connection or each vertex, each node failing with a given probability. We ask, what's the probability of overall failure over the network? And even though I'm talking about probabilities, probabilities can be written often as rational numbers. So you have an integer in the numerator, an integer in the denominator. And so in the end, the problem boils down to counting. Okay? And finally, the thing that we are most interested in is AI, applications in AI, specifically in probabilistic reasoning and other tasks where, again, the probabilities can be written as fractions or integers, and there, what we are interested in is evaluating a action strategy for, say, an autonomous agent that has the lowest possible probability of failure. So now you might ask, okay, if this problem is so widespread, why have I not heard about it? I work on AI. Why do not people talk about this? And the reason why people tend to sweep these problems under the rug is that they are very, very, very complicated. Okay? So here I show, from the formal point of view on the left, an inclusion Venn diagram of problems that belong to these different complexity classes. P and NP are classes that you are hopefully familiar with. They encompass many problems in optimization, in science in general. And the counting, NP hard also is this other class of hard optimization problems. And you see, sharp P is the class that contains all of the counting problems. And you see it's a lot bigger, and it contains many problems that are even beyond NP hard. So that's the classification that we do in a sort of theoretic way. But also in practice, if you try to develop algorithms and solve these problems, even in the average case, these problems are very, very, very hard. And I know because I hit my head against them for a number of years. So this is from a paper that I wrote back in 2018, where we, in fact, developed the fastest known algorithm for these problems. And even with this fastest known algorithm, we can reach maybe 300, maybe today 500 variables, not more. Okay? So we are approaching, with these problems, we are approaching a situation where the number of qubits that we have is roughly the number of variables in these problems for which these problems become really hard classically. So this is why this is an interesting set of problems to tackle, okay, with quantum computers. The bad news is that actually, if you want strict guarantees with quantum algorithms for these problems, we know that there are no-go theorems, especially this result here by Aronson and others, that shows that with Grover type algorithms, the best you can do is like a square root type or some root advantage and not an exponential one. But could we develop new algorithms that maybe don't work for all of the inputs, but they work on average fast? Okay, this is in the same philosophy as classical solvers for, say, satisfiability or graph coloring or other problems. We know these problems are hard in the worst case, but still we need to solve them somehow, okay? And so this is what the rest of this story will be about, and I will pass the mic to Victor, who will tell you about neutral atoms.
Thank you. So in going to towards practical counting, so first of all, before I get into the neutral atom, to give you an idea ahead of towards practical counting, the key idea is the following. We're going to use a quantum computer as a quasi-uniform solution generator. So this is going to generate uniform solution, quasi-uniformly solutions to our constraint problem. And then we're going to use these generated samples to approximate the solution count, right? So in the group, this has been tried using QAOA circuits in the digital mode before, but today I'm going to talk to you about the analog version that uses Rydberg atoms and the Rydberg blockade. And now, disclaimer, these algorithms are all kind of bad algorithms. If you try to get an exact count, they will work in exponential time. And so it's going to be trying to get an approximate count using these algorithms. So neutral atoms, the basics. Let's try to do this in 1 minute or two. Neutral atoms, quantum computers are, in my opinion, fascinating. They work by having rubidium atoms trapped in a vacuum chamber. These are going to be trapped using lasers that are going to create kind of these layouts that you see on this first image over here. So these layouts can be arbitrary geometries. Here you have a square geometry. And then you can use another set of laser to rearrange these atoms into the specific geometry you want. So here, a fully filled square lattice. Then you're going to use another set of lasers to excite these rubidium atoms so that effectively what you're going to be working with is this two-level system between the ground state of these rubidium atoms and a highly excited electronic state. It's still neutral, it's still an electron that's bound to the core, but it is one that orbits very far away from the core of the atom. And so when you have this other set of laser, the state of the system here will evolve under this Hamiltonian that you have here. So it has two parts. The first one is the interaction term, so Hint. This describes, in fact, the van der Waals interaction between highly excited Rydberg states. So this Ni here, if it's 1, that means that this atom is in the Rydberg state. If it's 0, the atom is in the ground state. So what you see here is this interaction strength, Vij, goes like 1 over r to the 6. At very close distances, that interaction is extremely large. And then the further you are, it decays extremely fast, okay? So in a nutshell, two atoms that are very close cannot be both excited in the Rydberg state. It's going to be highly prohibitive energically. The second term you have here, this local term, this can be modulated in time. And this essentially just corresponds to a global X on all of the atom that induces transitions from the Rydberg state to the ground state to the Rydberg state. And how strong that term is modulated by this omega here. You can think of this as only the power of the laser. So shiny laser works intensely and shines on the atoms. And when you have this Hamiltonian, you get then to this unitary evolution of the system that describes how the state of the system will evolve from its initial state to its final state, which you then measure with a simple CCD picture. So this is the readout that you get at the end. And here in this case, you measured, well, I have some form of a checkerboard pattern between the red and the green. And so all of these steps combined make this analog quantum platform. Why is this analog? It's because you are literally letting the system evolve to do what it does. So it is a quantum simulation in almost its purest form. You're letting the system simulate its system itself. But what we did is try to figure out a way to harness this for the task at hand. So let's get into that right now. And the phenomenon of the Rydberg blockade. So I said to you that the interaction is very strong at short distances. So imagine we consider these two atoms I and J and we put them close to each other. When they are both excited in this highly excited Rydberg state, this one state we will consider, their electronic cloud essentially overlap with one another. And that's going to be extremely prohibitive energetically. And it's going to prevent, in fact, this 1-1 state from ever being occupied once you're below some threshold distance. So we call this distance the Rydberg blockade that you can see here on the graph on the right. And so what this means is that if you are in a certain limit where the interaction between two atoms is much larger than the Rabi frequency, the power of your laser, omega, you have this definition of this blockade radius, and it means that every pair of atom that has a distance that is below this blockade radius will have the 1-1 state be completely prohibited. So what we can write is this effective Hamiltonian called the PXP Hamiltonian, where you can see that the PIs here are essentially projectors onto the ground state of the atoms. So here what it means is that the site I can only flip the xi. It can only flip it if all of its neighbors are in the state 0. So this is a strong constraint. So in effect what we've done is we've made it so that the low energy manifold of this PXP model is in fact this constraint satisfaction problem that we had at the beginning. So in this context, when we have these atoms in the Rydberg blockade, it forms a two-sat formula where you have this AND formula on all of the edges of not xi and or not xj, which means basically that this formula will only evaluate the true if the atoms are either 0, 0, 0, 1, or 1, 0. So you can see this in action. If we place a lot of atoms on the black screen, then we see that we have these blue circles are all of the Rydberg blockade radius. So all of the atoms that are within a Rydberg blockade radius of each other will have an edge. And on this whole system, you have a two-sat formula. And all of the solutions to this two-sat formula are nothing else than independent sets on this system. So they're collections of basically choosing a site as a 1 without choosing any of its neighbors as a 0. And the collection of these independent sets for a given graph can be very, very large. And on this, I'm going to give it to Joe.
So let's get into a bit of the nitty-gritty of how we actually start doing the counting. The keystone of our counting process is this observation that approximate uniform sampling is equivalent to approximate counting. A quick example of how this works is if we have a very simple SAT problem here, with 3 known solutions based on the 2 bytes, and we assume a uniform sampler over that, what we can do is we can construct this tree. And this allows us to traverse the tree in a way that allows us to formulate a count. So the way that this works is if we start with neither of the bits assigned, we can take our approximate uniform sampler, sample a bunch of these bit strings, and then record the probability that a certain bit is either 0 or 1. And if you do that, you take the most probable one, so in our case, this first bit being 0. You remember that probability, and then you resample, assuming every sample has this first bit fixed to 0. And if you do that, then you come down to this leg of the tree, and you see that it's a 50-50 chance of either it being 0 or 1. That's all you need to do to get an estimate of the count. And to calculate that is you just traverse back up the tree and multiply all the probabilities. So you take 1/2 times 2/3, that's 1/3, you inverse it, that gives you an estimate of the count 3. This generalizes to larger systems. Essentially all you need to do is build a bigger tree and then progressively sample and select the most probable bit. And as you continue this, you build up this telescoping series of probabilities. And again, it's just multiply and inverse to get a good count. This JVV algorithm has two very important constraints. The first being the problem is self-reducible, which means if you can take a subset of the problem and find all the solutions from that, it's good. Perhaps an easier analogy is if you can construct this tree and everything is connected. We get that naturally for Rydberg devices, so we're happy there. The other thing that this relies on is that we have an efficient, almost uniform sampling process. And this is the catch with a lot of the classical methods that use this same JVV, is you can get efficient samples, or you can get almost uniform samples. Getting the combination of both in a classical SAT solver is very difficult. So what is our strategy? Our strategy is, as Victor said, is to use the quantum computer as the sampler. And we do the simplest thing we can do on these devices. Given our SAT problem, we know there's a certain subspace of solution states. One that will always be there is the all zero state. So you initialize your system in the all zero state. You simply turn on the lasers. You wait until coherence time or some random time in there. And then you measure. And you do this repeatedly to build up the sampling distribution to estimate the underlying uniform distribution. And we just simply ask, how uniform is this superposition under this evolution? And can we use that to count the constrained solution space of our SAT problem? And again, just to emphasize that the self-reducibility constraint is built into the Rydberg devices. So in order to estimate how non-uniform our samples are, we can simply look at the distribution. So this plot on the left is a simulated evolution starting from the all zero state and go back. Yep. And on the x-axis is just every single bit string that you can imagine. So you can see that there's some bit strings, particularly over here, with no probability. Those are all the states that do not satisfy our SAT problem. And all the states that we see are the solution spaces. Clearly, under our very, very simple input method, we don't get a uniform distribution. So we have to modify things a little bit. Instead of taking a single input state, what we can do instead is you can measure, and overwhelmingly likely that measured state will be in the solution space, and then instead of starting from the all zero state, you can start from one of the other solution spaces. And when you do that, and you can show this pretty easily using Lindbladian dynamics, that after a number of iterations starting from a different state, the output distribution over all the bit strings begins to compress down to the uniform distribution. And if we want to quantify how accurate we need to be to the uniform distribution, the JVV gives some very nice constraints on errors and number of samples needed, assuming that your non-uniformity scales inversely proportional to the system size. So our plot on the left here basically shows that for a fixed input, you don't quite get the 1/n scaling that you would like for the JVV algorithm, but through this fixed input for different system sizes, you can see that it very quickly tracks down to the uniform distribution. So we have a uniform distribution, which means we can do some counting. We took a couple instances of random arrangements of atoms on a Rydberg computer, and those define a SAT problem. And so we simply simulate our device and record measurements, and through the bit string output, we can start to sample or estimate the number of counts in the SAT problem, or number of solutions, sorry, in the SAT problem. These instances are particularly interesting to us because it's the transition between when you need fewer JVV samples per step versus the number of solutions count. And so what we see is through a polynomial number of samples, we start to get a very good estimate of the number of solutions to each of these SAT problems. And now everybody likes to ask us, well, is this better than classical counting? And so through some generous but not unreasonable assumptions, we can start to ask, okay, what classical problems are very difficult to solve? And we know that for highly connected problems, such as a triangular grid, a lot of the classical SAT solvers slow down considerably. So what we can do is through some engineering estimates and some optimal error estimates, we can define the time to compute the solution count for some number of variables. And for problems on a triangular grid with a high density of atoms, the classical methods slow down considerably, which is this purple line here. And so again, through some assumptions, we can estimate the number of variables that we would need to start to see, quote unquote, a quantum speed up in the counting problem. And we find that to be around 2,000 variables, which is great because there's some experimental Rydberg devices that are already of that size, if not greater. Another important constraint that we should mention is some engineering challenges associated with getting to these system sizes. Victor mentioned the transition from the Rydberg model to the PXP model, and how well you can do that on an actual device also provides a limit to the system sizes that you can count. And so part of this XPRIZE, we're interested in some great extensions to this, one of which is moving to a 3D grid. Through 3D grids, you can get arbitrary SAT problem instances, and that allows you to kind of explore the entire Sharp-P space. We also need to do a little bit more hardware engineering and looking at the effects of further nearest neighbor interactions. And if we don't get quite uniform sampling, what can we do with that? And we can kind of get upper and lower bounds, so it's still a useful use case. And so in conclusion, we were interested in these counting problems because they're very hard and much harder than many of the other problems considered. And our algorithm on a neutral atom device allows us to approximate the count for large instances of these problems. And it's currently implementable on modern hardware, and through Pascal, we're starting to try and do some benchmarking with that. And I'll leave you with just an overview of some of the other great work in our group, and if there's time for questions? No?
There's
Probably.
not, unfortunately, but you'll have some more time at next break, of course.
Perfect.
Yeah. Thank you very much. So Joe, Victor, Stefanos. For our next presentation, let me introduce you to Maxime Dion, quantum software developer at the Algo Lab as well. He's going to talk to you about a project on limiting trotter infidelity bounds. So Maxime, all yours.
All right. Okay, I think you hear me better with this. Just to be sure I understand how this works. Okay, good. So what I'm going to present to you today is an Algo Lab project I've been working on, and also want to highlight the participation of Abdallah Tounsi, who was an intern. He's completing his PhD at CS Tech in Algeria, and also Ludovic was an intern with us also last summer. So you've seen this formula a lot today. So this is time evolution under an Hamiltonian. And if you want to actually construct this operator, what you need to do actually is to diagonalize the Hamiltonian. Okay, the Hamiltonian, you need to diagonalize it, even if you want to do it on a quantum computer. Something you can do, however, if you don't know how to diagonalize it, is to write it as a sum of different parts, okay, sub-Hamiltonians, that are easier to diagonalize. For example, polystrings could be a good idea. This is mostly what I'm doing. And then you can approximate the time evolution with this formula, where you apply all these Hamiltonian, these evolution one after the other, and then you get an approximate evolution. And this approximate evolution is close to the actual one, but you're committing an error by doing this. And what is this error? So there is a paper by Childs, a famous paper by Childs, that tells you that you can actually bound this error by computing the distance between the two evolutions and computing computing a bunch of spectral norms, and you are able to bound the error that you're making when you're doing this trotterization. This is important because if you're going to use time evolution in an algorithm, you actually want to know what's the error you're making on this. And as you can see, the error grows with the length of the evolution. So if you want to limit the error, you need to limit the time of the evolution that you're doing. So for example, so another way that you can use to characterize this error is actually to compute the fidelity. So here I'm looking at this state. So this would be the exact evolution state, and this is the approximated one. And then what you can compute is just the fidelity, just the scalar product between these two. And here on the plot, what I'm showing is that I'm looking at the infidelity. So you can see that if you use a child's bound to compute the fidelity, you get this green line. But if you look for it here, I'm looking at a very simple Hamiltonian, only 4 qubits and 19 polystrings. And you look at the worst case scenario that you can get is this blue line. So you see there's quite some room between the bound that Charles provides and the actual error that you're making in the worst case. So also something that is important is actually you can bound the infidelity with the bound's child, the child's bound here, just like this. So the infidelity is also just 1 minus the fidelity. So looking at this, you see that you might be able to find some improvement, and that's what the old project is about. So the way we're looking at the error, the Trotter error, is through this phase factor operator. So here, both evolution approximated and exact are unitary evolution. So you can construct a unitary using this, and this is the phase operator. This is the Hermitian operator, and you see how you can construct it. This is the approximate evolution, and this is the inverse of the exact evolution. And also, you can use this operator to directly compute the fidelity if you want. And also, what we're going to look at are this eigenbasis of this operator. So the eigenbasis of operator of the phase factor operator is the same eigenbasis than for the phase factor operator, the phase operator. So we're going to look at this eigenbasis because it has some interesting properties. So the first property that I'm looking at is that these eigenstates, if you evolve them, so here this is the evolution under the approximate evolution, this is the bras of the evolution under the exact evolution. You compute this, you see that this is equal to 1. So what I'm telling you is that these states, if you evolve them in the exact evolution or you evolve them with the approximate evolution, you don't make any error with these states. So these states have this particular property. Another way to say it is that if you evolve with one or the other, you get exactly the same state. The only difference between the two is the global phase. Also, maybe just to make sure that it's pretty clear, is that this X dependence here is not a dependence on time, it's just a dependence on the length of the evolution. It's quite subtle, but it might not be so important here, but anyway. So something that you can do, is make some great figures. I call it the Sauron's eye. This is just a polar plot of these phases. Okay, so each eigenstate has a specific phase, and here, the radius is time, or the duration, I would say, and the different lines are the different phases. So this is one nice way to look at it. You can also plot it in more in a Cartesian way, so you see how the phases are kind of going away from the zero phase like this. And also, you can see that this looks like a bit like a quadratic function. And actually, if you know about Trotter error, you know that the error that you're making is a quadratic. So something you can do is just divide by x squared to get something like that. And why I'm doing this is because I want to bound the error in some ways. So in looking at this, and maybe I can try to compute what is this value up here and the value up there. And we'll see that this is important. Also, you can take these eigenvalues and put them into an order. So I label the smallest one, the negative one, actually 1, and the last one is the positive one. So here is maybe the first contribution to the work is this. So you can show that you can actually construct a state that maximizes the infidelity. So the worst state, that's why I call it the worst state. The state that is going to create the most error when you're going to evolve it. And to do this, you just need to make an equal superposition of the two of these eigenstates. And you need to pick them in a way that they have the most opposite eigenphases. So for example, if I pick this state here, I will need to pick probably this one here. Okay? And if you construct a state like this, you get an infidelity that goes as the difference between the two eigenphases. And you see if that are opposite, this you get pi over 2, and sine of pi over 2 is 1. So you maximize the infidelity. But for shorter times, for small times, you can see that actually if you want to maximize this infidelity, you just need to pick the lowest eigenvalue and the highest eigenvalue. So the red curve and the blue curve. And this is the infidelity that you get. And if you're able to bound this operator, then you're able to bound the difference between these two phases. It's just twice the norm of this phase operator. And then you have a bound for the infidelity. And if I show you how it looks, so on this plot, you see that this is the bound that is provided by Childs, and in the red dash line is this bound here. So it looks like we've done like something that's very, very nice. We have a bound that is very, very much closer, and we have a better, we have a better estimation of that. But there are some fine prints. So this phase operator, you can deconstruct it, you can decompose it as like a Taylor expansion. And the thing is that this Taylor expansion is an infinite sum, and also it has a limited radius of convergence. I don't want to get too technical. And also all these operators here, these you can construct them from the part of the Hamiltonian and computing like a nested Hamiltonian, commutator of the Hamiltonian. And it gets pretty bad pretty fast. And the computation of the norm is not very practical. So it's kind of difficult to try to bound this, and I've been working mostly on trying to bound this phase. So I'm trying to bring like a workaround. I don't know how much I'm doing on time, but okay, I'm pretty much done. So one thing that you can look at, and maybe an idea you can try to exploit, is that it would be much easier to compute if you could say that this is smaller than this. So this is like kind of wishful thinking here, like how is this even possible? Like if you pick an Hamiltonian, you can compute this operator, and you have no guarantee that this is going to be smaller than this. But maybe it's possible. And the reason why is that, and I'm not sure it's possible, but when you construct a Hamiltonian like that, and then you construct the approximative evolution, you have a degree of freedom on what is the ordering of these operators that you're doing. So here in the sum is commutative. So here I can define different approximate evolution by changing the order of the Hamiltonian. And this changed also the phase operator. And here I'm just going to give you a very small example. So this is a 2-qubit Hamiltonian that is very problematic for me. But if you use some order, you see that this would be the bound that you would compute with just this term. And then you see that actually it's not a bound at all. You have phases that goes above and beyond. But you just reorder the part in the Hamiltonian and you get this. And now you can compute this black line here and there, and then you have bounded the phase. So by changing the order of the operator in the Hamiltonian, it might be possible, but I'm not sure if there's always an order like that you can do this. So what's next? Exactly this. We want to see if there's always an order that will satisfy this property. Also, computing spectral norm, I don't know if you know, but it's very difficult. You need to diagonalize your operator. So we look at practical ways to do it with some approximation based on the trace. And also, like in Trotter evolution, what I've shown you is first order, but if you go to second order, you can do other stuff. It's much more precise, and we didn't look at the conclusion of applying this scheme to this second order trotterization. So on that, thank you for listening.
We have time for one question, if there's one. Yep, we've got one.
This one? No,
can you repeat the question?
Yeah. So it looks like the bound is pi over 2 and minus pi over 2. But here, what I'm plotting is not the phase; it's the phase divided by the time squared. So I don't know if it's related, but maybe it's just a but yeah, but if I come back maybe to the way that I've shown you the first time, so here you see that actually you're bounded by this is really the phase, and this is kind of bounded, and it's also something that I'm exploring is that when you go at very large time, all these phase tends to just uniformly distribute around the unit circle, and maybe also there's some important information that we can take out of this when you go to very long time.
Thank you, Maxime.
Thank you.
So for the next step of our day, it's a panel, and we will welcome on stage students that have put in place or at least are participating into quantum clubs in their universities. So please, Florence Paquette, and I need my paper for the other names. So Florence Paquette from Sherbrooke, Félix Wilhelmy from ETS, and Arjun Dixit from U of T. If you want to join me on stage. Good. Well, welcome to this panel. So first question, well, can you tell me who you are, what are your studies, and what department, or future studies, if it's the case? So, well, let's start with you here.
Yeah. Hey, I'm Arjun Dixit. I'm a third-year undergrad studying math and physics at the University of Toronto. And I'm currently a communications exec at the UTQC, which is the University of Toronto Quantum Computing Club, and hopefully I plan on doing a PhD in quantum computing in the future.
And for how long have you been in the club?
It's been a year.
A year, okay,
Yeah.
great, fantastic, thanks. Well, welcome to the panel.
Thank you.
Hi, it's good, okay. My name is Florence, and I'm a student in the Quantum Information Science bachelor degree here at Université de Sherbrooke. And I'm graduating actually this year in December. And after in January, I'm starting a master's degree in statistics. And my research project will be about quantum computing for finance.
Good. And you are part of a quantum computing club here?
Yes, of course.
That you have founded with other people from the bachelor's degree?
With another guy from physics, actually.
Oh, okay.
But yeah, we have many disciplines in our club.
And what's the name of the club?
The name of the club is Quantus.
It has to finish by US, right? But
yes,
not US,
exactly.
US here.
Yes, US for Sherbrooke, of course,
okay.
yeah.
Yeah, and what about you, Félix?
Hello, my name is Félix Wilhelmy. I'm a master's student in quantum machine learning at ETS. I have been for like 2.5 years in my student club, which is Quantum ETS. I was the captain, and now I passed the torch, and I'm the vice captain of my club.
Okay, and well, before talking about the clubs themselves, can you tell me what brought you to quantum computing? Because I mean, it's well, not a clear path from well, elementary school to high school and so on to end up, if I can say so, in quantum computing. So what brought you to the field? If we start again here.
Yeah, I mean, it's kind of funny for me because when I first joined U of T, I was trying to become a mathematician. And then second year start, I wanted to become a string theorist for some reason. And then I just found quantum mechanics to be really interesting, like the course. So then I took quantum information with another professor, and then it really sprouted from there. But it took me a while to like find this. I didn't find this in high school or like early on as well. So it took me some time.
So through some courses you got at the undergrad level, right?
Yeah.
Okay,
exactly.
good.
For me, so when I was in Cégep, like my favorite classes were like the physics classes and calculus. So I decided that I wanted to include that in my future. And I'm also someone who really like multidisciplinary things. I always like to work on a lot of things at once, and I like to take on projects that includes many disciplines. So when I was like scrolling on internet to find a degree, I saw the quantum science program, and from what I was looking, it really looked like something that would interest me. So I just decided to apply, even though I did not have any prior knowledge in quantum computing whatsoever.
Good, thank you. And Felix?
For me, it's a little bit more random and a little bit a funny story. I was near the end of my bachelor degree in software engineering at ETS. I had difficulty fitting course in my schedule, and actually the only course that fit in one of the semester was Introduction to Quantum Computing by Olivier Landon-Cardinal. And he made me fall in love with the quantum computing. I really love it, like the more challenging aspect of and how you had to think differently. And also it felt so open, like there was not a lot of explored, and it was like there was so many things to discover. So I think that's like why I got into it.
Interesting. And then what about the club themselves then? What brought you to the club, or what did you, why did you like put it in place in the case you were the founders? So maybe Felix, we can start with you.
Okay, sure. Well, in the same course that I had taken in introduction, I met Samuel Richard and Simon Roy, who were the founders of the club. The club was kind of like very young, I think 1 year old. It was just at the beginning, and quantum computer was not very popular, I feel, at that time, especially like at ETS. So there was like kind of a startup feeling, and those two people, they were pushing themselves and like doing so many things, and it really inspired me, and like it made me want to join up and participate. And I'm also a very competitive person, so I wanted to join the competition like immediately and started organizing and leading the charge for this aspect of the club.
So if you say that it was not that popular at the time, I mean, that was not 15 years ago.
No, it was not popular, but like the introduction course was just starting. It was not even like actual. It was like a special course. It was not like named quantum computing, and like there was not a lot of thing to go with. Everything had to be done from scratch, and we had to do it on our own.
But then it means that it grows fast, right?
Yeah. We had the wind in our sails, and like as the Quantum Institute at ETS arrived and so many things, we even got more wind and more like motivation. It was really fun to like, and it's still super fun.
Great. Florence?
Yes. So for me, like 2 years ago, I participated in a hackathon at ETS, and I met Julien-Pierre Hull, who at the time was a physics undergraduate student, and we threw around the idea of maybe one day starting a quantum computing club. We were sensing that in our programs, he in physics and me in quantum information, we had a lot of interest that was growing for this domain, so we kind of just threw around the idea and then didn't do anything. And now, 2 years later, we reconnected this summer, and now I think we're both more confident in our abilities to lead such a club and manage events. So we just, and also we saw that a lot of students were motivated and they wanted to participate in a quantum computing club, so we just decided to do it like 3 months ago.
And then how many people do you have in the club now?
In the club, I think officially we have like 30 people right now. And in an event that we participated in Calgary, it was a quantum hackathon. We had 15 students that participated.
Flowing to Calgary from here?
Yes, exactly.
Wow, that's good, great.
Thank you.
And what about you?
So I like learned about the club when I was taking a course on quantum information. So like I talked to like the president at the time, like Shaswat, and like a few execs like Michael Silver, who's now the president of UTQC. And then we literally like they told me about the club and how as like a community it's a pretty great place to be, because unfortunately U of T doesn't really have like an undergrad like quantum computing like program or like something specific. So the club was kind of like the only place you could go and like talk to people who are interested in quantum computing. So then I joined the club, and then it's been going pretty great so far. Like now I'm part of the executive team and like leading events or like taking part in stuff. And coming here, for example, is like one of those and talking about the club overall. So it's been pretty great. But the club's been around for a while though.
Okay, and how many people is there?
It's like must be like 800 people. Like it's like in the hundreds for sure. Like I don't know the exact count, but there's a lot of people.
That's many people. Yeah.
Yeah. That's a lot of
I can guess you
Wow.
you lose count.
Exactly. Yeah.
That's good. And well, can you give us examples of well activities or events either you participated to or you like set up from ground?
Well, like UTQC does a lot of stuff. For example, like every week we host like a Q-Learn session where like people come in like give talks. So for the fall sem, like the sem right now, we have like the exec team like talk about like basic quantum computing principles and like basic examples of algorithms or like teaching like basics essentially. And then next sem we'll have people from across industry and academia talk about their research, like cutting edge research, and then people interact with them, they network, and then learn a lot as a community. And outside of those like weekly like lectures or like sessions, we also have like Qiskit Fall Fest, like hackathons, like QSci, which is like one of the largest conferences in North America for quantum computing. And essentially through these activities, we like kind of build a community as well. And that's like the biggest idea I think that we have at UDQC is like to build a community for people to engage, or like even have like a platform through like Discord, or like you can email all the execs about any problems or like any confusions, or like any like if you need any resources in quantum computing, you can always reach out to me or like the president, and we'd all be like very happy to help you essentially.
So you get 800 people calling you all the time?
No, luckily no.
It's good. Florence, what about you? What are the events you participate to?
So we have like two main activities, I would say. We have our monthly meetings. So in these meetings, someone or a group of people from the club will present a subject related to quantum computing. And it doesn't necessarily have to be something technical. It can be, but it can also be students that present experiences and opportunities that they've had in the quantum ecosystem. So for example, we had a presentation from students who shared their experience of a first hackathon in quantum computing. So they can share like what they liked, what they disliked, how it was for them, and so it can entice other people to participate in these kinds of events. We also have the more technical presentations where some people will present some algorithms. Or we have also some workshops, for example, to learn libraries, to learn how to program a quantum computer, for example. So it's really like presentations related to quantum subjects. And of course, we would like to have some events where we have some professionals that come talk to us and give us their insights about quantum computing. And also other experiences that the people in our club have had in the quantum ecosystem. So I would say that's one of our main activities. And the other one is to, of course, participate to quantum-related events, especially hackathons. So as I've mentioned, we've participated in Calgary in October, and we're now going to the MILAC, I think next week, next Friday, and we try to like stay on track on about what events are happening and to get as many students there.
So MILAC is a hackathon next week in Montreal
Yes.
at Mila, right?
Exactly.
Good. And what about you, Felix?
Well, our staple activity that we organize is each semester we do 3 workshops. One is the introduction in quantum computing very generally, because on our side, it's mostly like software engineering student, undergrad students, so they have less of a clue about quantum mechanics and quantum computing, I feel. So we take the time to give them an introduction, and then we have a workshop about programming, in quantum computing programming, and then a more theoretical workshop. And then also we participate in hackathons, like the main one we participate, I think, are the IQ Code Fest, the MIT IQ Hack, and then the Y Quantum at Yale. Those are the 3 ones, and then there are some sporadic, but it takes a lot of time to organize participation. And finally, big point that and a big activity that we're organizing, and that is actually happening tomorrow. If anyone is interested, it's open to everyone. It's in Montreal at ETS, for the QuizKid Fall Fest 2025. We are organizing a big conference, and we'll have like people from Algolab who will be speaking, but also like Gilles Brassard from Université de Montréal, Victor Drouin-Touchette from Sherbrooke, and Jacob, and many more. So yeah, that's pretty much the activity. And also, just want to reiterate, if anyone is interested, you can come ask me for information after. Sorry for this.
Yeah, this is the place to talk about all these things. So, well, thank you very much for this talking about this event of tomorrow. Maybe a bit more of information about the IQ Code Fest. So this is the hackathon you were talking about before, Florence, that was in ETS 2 years ago. Then last year was in Polytechnique Montréal. For the students in the room, you can expect to have one more of these hackathons for students coming this next May or June, probably June. But if you want to have all the information, either, well, stay tuned to, Institut Quantique's information coming out, or you can write to Tom, who will be, more than happy to give you all the details when they come out. We don't know the date yet, but it will come back next spring. And on your site, Arjun, you talked about the Q-Site activity. I had the chance to participate last year. There was like tons of people over there. I know that some people from the ETS club was also present. So, can you talk maybe a bit more about this event that was like, more than just for specifically students at the U of T, right?
Yeah, I mean, Q-Site happens like pretty frequently, like every single year. It's been happening for a while. So every year we collaborate with the University of Toronto and the CQIQC, which is like the Center for Quantum Information and Quantum Control at U of T, and we like get a space. We have like a conference, like we have people coming over from across Canada, like give talks. We have like hackathons going on as well. It's open to like everyone. You don't need to be like a postdoc, like grad student or anyone. Like, you can literally sign up. You can be fresh out of high school and even literally take part. And you can take part in the hackathon. You can at least learn about stuff as well. Like, that's the minimum you can do. So it's a pretty nice like community building place. That's the whole idea of like a lot of stuff we do at QTQC in Toronto as well.
And it usually is in September, right? October.
Yeah. This year it kind of got a bit messed up. It's gonna happen next sem, like in like March, April maybe. Like normally it happens in September and October though, but this year it's kind of different.
Okay, so stay tuned if you want to participate for more info to come out, right? Okay,
exactly.
Great. So why is it important to have students club like the ones you are participated in?
I mean, quantum computing is pretty emerging in that sense. It's not like very it's not very structured, I would say, at least on an undergrad level, for like at U of T especially. So like building a community, like I said, is extremely important, because otherwise, if you don't have anyone else to engage with or like network with or like learn from, then you kind of like lose like touch of what you're doing, and like it's pretty discouraging. So unless you're like a grad student who obviously has like a professor or like a mentor, or you're working in like a lab with a PI who can obviously guide you or like talk to you about this, like we as like undergrads have to like kind of do it ourselves with each other. Then obviously we also engage with industry as well, so like keeping in touch with how quantum computing actually is out there in the real world, not just in like a textbook. So I think the club really helps in doing that, and also in helping skills as well through like hackathons or like sessions as well, where you can like learn stuff. So it really helps in that, I would say, primarily.
Good, thank you. Florence?
Yes, so I think that here in Sherbrooke, we have a very special ecosystem, right? We have the Quantum Institute with amazing professors, professionals, and students. And we also have the Zone d'Innovation Quantique with amazing expertise in quantum computing. So I think that having a quantum computing club for students is just the logical order. And I think that they can really help students make a place for them in this special ecosystem and make them feel like they're a part of it and that they're important. So that was, of course, a very important goal for us. Also, I think that sometimes as a student, it's hard to stay on track of every opportunity that you have. So for example, last year I was talking to someone in your club, and she was telling me about all the opportunities and the hackathons that you were participating in. And I was like, oh my God, I never even heard of that. So I thought to myself, like, I'm missing out on so much, and I want the students that are part of the club to not miss out on those opportunities and have the chance to participate. So that was also very important for us. And finally, I think that quantum computing at first can be kind of intimidating if you don't really know what it is. And also seeing this big ecosystem, it can be a lot for someone who has no knowledge in it to just say, hey, I want to learn quantum computing, I'll do it on my own. So I think that creating a club where you'll never be judged if your level of knowledge is not like impressively high. We just want you to participate, learn, and if you're interested, no matter what your background is, you're welcome. So creating this kind of safe space, I think, for people to just feel comfortable in learning quantum computing was a very important goal for us.
Thank you.
Well, for us in software engineering at ETS, people don't really know what quantum computing is. So a big part of our activity and the workshops are made to spread awareness about what is quantum computing and to show that to the students that it's not something that is like a galaxy away from them, and they can actually like do something. So this is the main part, I think, for what we do. We got so many students involved. Like there are natural steps. Like after you get involved, you can get into research. You can start interning in labs. You can do many things, and it's a different type of vibe. But yeah, at the beginning, on your first step, it's like the students club are really there to help you, and then they can also allow the students who want to really get more involved to do much more and grow into the roles. And like it also helps with leadership, I feel, later down the road when you get involved in the club.
Good, well, thank you. And what would be like famous last words you'd have, or what should we be aware of coming up soon? Like either of the two questions you can answer. So famous last words for this.
We finished? Yep. Oh, okay. Well, actually, there was another question that I really wanted to answer. So
okay, you can answer all the questions I've not asked yet. Yeah.
So this was one of the important part, but I think the Quantum Student Club also another very important thing is that maybe it's a little bit less felt in Sherbrooke and in the quantum computing research group. But a lot of the students that are grad students, especially master students, are not always in research group in quantum computing, and they are very alone. And sometimes their teachers or the professor, they are starting to learn quantum computing with them, and so you're kind of lost, and you're teaching your professor about quantum computing, and you don't know how to read this paper. So not just a club in one university, but I've often, like with other university, created community via the student club, to opportunities to help each other understand and go through and like create this network of students. So I think this is another very important. So this is my famous last word.
Thank you very much. Florence.
Okay, so I would say if you're interested in quantum computing, or not even fully interested, just curious, come to our meetings. Come see us. We have a meeting once a month here in this very auditorium. You can look up the schedule on the horaire of the Institut Quantique. And no matter what your background is, you can be in physics, in maths, in computer science, in finance, in chemistry, in bio. I don't care about your background. If you're interested, you can come see us, and we will always be open. So yeah, I just encourage you to, you can write to me if you have any more questions, and come see us.
I can remember your first meeting was in the room two floors above, and it was so small with comparison to the number of people that were in the room. So this is why you are now in the auditorium, right?
Exactly.
Yeah. That was interesting to see. And what about you, Arjun?
Yeah, I definitely agree with Florence. Like, if you're not part of the quantum computing community, or at least if you think you're not, like, you can literally reach out to anyone, like, literally wherever you are, wherever you're based, and I'm sure they'll be happy to, like I don't know, talk more about it. Like, especially the clubs, like the three of us, like all the clubs we lead, or like we're part of, pretty open, pretty like building a community essentially. And I'm a pretty big example of that because from being like an outsider, like less than a year ago, to like coming here and then also having a poster presentation on this, just because I met my like supervisor at the club, like he was giving a lecture and I essentially talked with him and networked with him. So I kind of did it myself. So I kind of know how it feels like to being like an outsider, like not being part of it, and then obviously feeling like you're part of the community and like feeling like you're there essentially. So like just stay strong and just don't hesitate essentially. Reach out to whoever you would think you should reach out to, and I'm pretty sure they'll help you.
Great. Well, thank you very much. So, Arjun, Florence, Felix, thanks a lot for your insights on quantum clubs.
Thank you.
Thanks. A lot. And with this, it's now time for the break this afternoon, and we will reconvene at 3:15. I'm sorry, 2:45. 3:15 is too late. 2:45. So everyone, it's time to go back to your seats. So I promise you the beer is now cold, but we still have to go to a few presentations before that. So let's roll with the rest of the program of the day. So for this next presentation, I will introduce you to Dominique Marchand, Special Projects at 1QBit and COO at Irreversible. Also, Sophie Rochette, she's electronic physicist, lead at Irreversible. They will talk to you in two parts. Part one will be automated quantum design and accurate resource estimation for fault-tolerant quantum computation. And second part will be analog hardware for artificial intelligence in highly constrained environments. So, Dominique, you're first presenting on behalf of 1QBit and Irreversible. All yours.
Thank you. All right. So apologies for putting so many words in the title for you to read. This is a little bit of work. We were asked to tell you a little bit about Irreversible, which is a company that was founded last year at the heart of the Innovation Zone. So our headquarters is in Espace Quantique 1. But we thought that it'd be interesting to tell you a little bit about its origin. So Irreversible is a chip company where we're rethinking efficiency for AI. So we're designing ultra-low power chip for AI. But we do have quite a few connections to quantum computing, quantum technologies. And one of them is being incubated. It was created inside a startup company that does quantum software. So we decided to split the presentation. First half will tell you a little bit about the company that created Irreversible, and then Sophie will take the second half and present Irreversible and what it does right now. I used the slides that were prepared, most of the slides were prepared by 1QBit CTO. They were quite technical, and there were a lot of them. I cut them half, so I think we'll have to skim a little bit over what's there. And I don't have animation here, so you'll have to bear with me. Before we jump into the technical stuff, I wanted to make some observation about my time there. One of the things that I came to realize when I was working at 1QBit is the fact that going beyond our tools, the limit of our tools is extremely difficult. It requires a lot of energy, and it's especially true if you're doing something that's quite difficult. And it doesn't matter if your tools, you're talking about carving tools, you're talking about mathematical tools or software tools. And building utility-scale quantum computers is a very difficult endeavor. It's something that will take a lot of time. Usually we present it as of the order of building a new CERN or building a new International Space Station. So a lot of energy, billions of dollars of investment, and many years of work. And yet, the tools that we have to do that right now are quite crude. Many of those tools right now are only talking about logical qubits. They don't have much predictive power, and they're not really automated. So we decided to try to address that. So if Steve Jobs was here presenting what 1QBit does right now, I would probably say 1QBit is doing three things. We're doing a quantum OS, we're doing next generation quantum resource estimation, and we're doing design tools. So if you've watched Steve Jobs present the new iPhone, you'll just repeat those three things 3 times, and you realize this is one product. This is TopCAD. I'm not Steve Jobs, but I'll jump in and try to do my best to tell you about what we do. So let's start with Quantum OS. So Quantum OS is really, and TopCAD is in blue here, the section. It's basically all the set of tools that are between the user space, this user program, and this execution environment. There's quite a bit of complexity here that's just summarized very briefly. You'll see, some of you will realize that we're talking specifically about a fault-tolerant quantum computer, and we're considering the special case of surface codes. But TopCAD can support other ones, and there's some work to extend it to other codes. Right, so I'm going to tell you a little bit about, we're going to borrow a little bit from the classical computing environment because there's some of those things that are not quite standard yet. And I want to tell you about the different level of abstractions that are happening between the two. So between the quantum program that you're writing in the quantum programming XDK or libraries that gets synthesized into a program, into a circuit that you want to execute, and other steps that need to happen before you're talking to a QPU, the actual qubits. On that side of the program, you do have to have talk to a controller, and talk to other components that will be relevant for the for error correction. So it's much more. There's much more orchestration that needs to happen on that side. It's not as simple as just doing the operation that you have at the beginning. So if you look at this graph, IR here means intermediary representation. So we start from that logical circuit. Now we do need to do quite a bit of interesting things with this optimize, compile, and prepare that circuit for the other end. When we're talking about those level of abstractions that are here, I'm talking about architecture. So an architecture in quantum computing, in computing in general, is this abstraction, how things are organized to execute something. Now, two things that we find on the classical side are instruction level abstraction. So basically, it's just a set of operations you can do. Now, but you can also talk about the microarchitecture. My microarchitecture is all the components you have inside a processor to do those instructions. So you might have multiple floating units, you might have integer units. Those various things will be useful for executing what's those instructions that are part of the instruction set. But because we have error correction, because there's an extra level, we can't write a microarchitecture. We don't care only about a microarchitecture that cares about physical operation on physical qubits. We have to introduce something else. So we'll talk about another microarchitecture, so a logical microarchitecture, and I want to show you a little bit what it looks like. This is supposed to be an animation, so the graph is not super relevant, but I'm still going to use it to try to convey how we get to what we mean by microarchitecture. So because we need to untangle, let's start from the fact that we have a surface code. So instead of working with physical qubits, we're working with patches, which are a regroupment, like groups of qubits that can encode logical qubits. But you do need to make operation between those patches to untangle them, for example. Now, if you want to untangle things that are between patches at different position of this, then you need to have long-range interaction. So you need some qubits that will be useful for entangling. You need some patches, sorry, that will be useful for entangling distant patches. So it sounds a little bit like a bus because you're communicating information. So what I mean by microarchitecture at this point is patches that will be representing logical qubits, but also assigning them some roles. Some of them will be, for example, a bus. Others might be used for computation. Others might be used for generating advanced states that are going to be consumed by the computation. So I think on this slide, we see a little bit what this looks like. So that microarchitecture is not just how do we build qubits, but it's also decided what they'll do. The way we're doing this right now is break down the logical microarchitecture into different modules that we'll use. We have some modules that are needed for generating states. Other modules will be used for consuming those. So basically, we organize them into subgroup or subsystems that have input and output. So that means that when you connect them together, essentially now you have a supply chain problem. You have to optimize so that enough states go in and at the same rate as state goes out. You can go even a little bit further, and there's a space-time trade-off at some point if there's an oversupply or undersupply of those states. So I'm not sure if I can use this. Oh yeah, there we go. So all of those patches here correspond to patches in the surface code, but the color here basically convey what we're using them for. So the green one are bus patches, and they're used for entangling or carrying information. You have other ones that are used for computation, and we organize them into groups like this to build the architecture. So really the microarchitecture on the classical side is something that's fixed typically, but on the quantum side, it will depend on various things, and it's set up by the operating system, by TopCAD. I mentioned instruction set architecture. I just wanted to point this has come from a well-known paper. There's quite a few choices. And we see that they're basically gates or operation you can use. This is the instruction you can run, but what is also interesting is that it also requires some specific advanced state or complex state that are consumed by some of those gates. So those are the magic states. That's why in the architecture I showed you just before, we have some sections that generate those states and other sections that consume them later on that architecture. So there's quite a bit of complexity, and then you can add even more. I won't talk about this slide. But just to tell you that once you start wanting to run a very large circuit, then you have more and more of those subcomponents you have to somehow distribute, and trying to route things properly and fit everything on one chip becomes quite challenging. So if you do this by hand, basically, there's no point. There's no chance. So that's why automating this process and And doing it for a specific type of noise that you have is very important. How am I doing for time? Another 5 minutes. Okay, go. I was feeling like I needed to run. I have 5 more minutes. That's perfect. There's an interesting paper. If you want to learn more, there's an interesting paper that was put together, and then it adds one level of complexity here. It's very important to understand the noise you have on your qubits. That will change potentially the distance code you're doing, which means will change what the architecture looks like and how you'll set it up. So all of this has to be chosen dynamically. So I don't want to say too much more about this, but this is a pretty massive paper. There's a few interesting things. One thing I learned from that paper is that when you're building qubits or when you're doing gates, usually what matters is not the average qubit that you have, it's really the worst. So it seems like the performance are pretty much dictated or predicated by the worst qubits that you have. So all of this basically needs to be taken into account. If you have a good understanding of the noise, then you can do a good programming and good microarchitecture, and that means that you'll have the best possible outperformance you can from that combination. All right, so I told you that what we mean by TopCAD as a quantum OS, so all those operations, building the architecture, and at the end of the day, what operation we can run so that we execute a program as efficiently as possible. Well, you have to do all those same steps if you want to do proper resource estimations. If you really want to know how long it'll take to run something, you need to do those same type of optimization. Like you want to shorten your circuit as much as possible. You want to then compile it. You want to transform it. You have to know what type of error code you'll need, and then decide where you'll put your magic state factory and all the components you need. So all of this you need to do, but once you have that, then you can really predict how long it'll take to do a specific circuit on a specific architecture. So the same tools are involved here. We're writing the noise profiler. That's also very important. That will feed into an emulator that will give us the information to try to decide how big we're doing, how big the distance of the code that we need for running a specific thing. So it's just another view of the same architecture, but we don't do the actual orchestration and scheduling of the operation at the end of the day. We're just predicting how much resource will be needed. So on the left, we have logical resources, so computation size, so number of operation, system size. That's what usually you do if you do only a logical resource estimate. We've run the same thing for a bunch of our algorithms that are taken from DARPA Quantum Benchmarking Program. That's what came before Quantum Benchmarking Initiative. And then we were able to transform that graph here from the left here, where you just have some comparison. So if you're looking at those points, you can say, yes, just this point will take more time, more qubits than this one, but you don't know exactly how long. We can tell you for a specific type of hardware. This one is something that we call target hardware parameters. So you can run this whole thing, this whole graph for various type of hardware, and then therefore figure out if such improvement onto the hardware will result in improving the type of performance you're looking for. Also means that if you know what your coherence time is, you can draw a straight line to show, like on this horizontal axis, to show what's inside and what's not outside. Whereas if you're trying to do this on the left, it's a weird shape that's really difficult to predict. So by using TopCAD, you get a whole bunch of predictions like this. So and just to say a word about using this as a design tool, it means that if you can use it to figure out or to predict performance, but you can also use it to give you some target for some of the parameters on the hardware you want to have to reach certain performance. So that's why it's used as well as a design tool. So when Qubit has been founded in 2012, it's been around for quite a while and spin off a few companies. And like today, we'll tell you a little bit about the Reversible, which is the latest one of those. But you might have heard about Good Chemistry as well. That was spin off a few years ago, and that was acquired by Sandbox. We worked with quite a few different partners. We started being more on the application side, and then realized that there was a lot of need for tools, and that's when we started working on TopCAD. Maybe I'll pass it to Sophie here to talk a little bit about what we're doing at Irreversible.
Great. Oh, working. Perfect. Yeah, so we heard a lot about the 1QBit's research and how it led to the creation of several other companies, Irreversible being one of them. I'm going to use my French accent because I keep tripping my tongue when I try to say it in English, so it's going to be a bilingual this time. Anyway, Irreversible, yeah, I'm going to talk about the work we're doing in developing analog hardware for artificial intelligence in highly constrained environments. So Irreversible emerged at the intersection of AI for quantum research and quantum for AI research. And what we found at its intersection is really stringent energy and latency constraints. To give you an example, on our AI for quantum research side, we were trying to develop at 1QBit a cryogenic neural decoder, and the specific circuit to perform the decoding needs to be put inside the cryostat for best performance. So it means that it needs to dissipate very little power, so it doesn't heat up the quantum processor. Also, it needs to process the syndrome measurement really fast to keep up with the qubit current time. So this is one example of how those energy latency constraints come in. And this points to the need to develop very specialized and efficient computing paradigm and hardware for implementing neural networks so that we can meet those energy and latency constraints. And it so happens that those same energy and latency constraints also are at the core of the current trend towards adding more and more intelligence to sensors and to device, and moving away from the cloud-based data centers processing for AI. And so that means that the specific hardware we're going to use to integrate AI and intelligence on those devices needs to be adapted to battery-operated device, low connectivity constraints, privacy, and response time concerns. So really stringent constraint, once again. And at Irreversible, we believe that the best hardware to do that is actually analog hardware. And it's not digital, it's really an analog paradigm that's going to help us achieve those targets and meet those constraints. Before we dive into the digital versus analog aspect of things, let's do a quick neural network 101, so we're all on the same page. So a neural network, basically it's an arrangement of neurons that have specific values that are arranged in layers and that are connected by weights. And those weights represent, if you want, the strength of connection between different neurons. And the value of those weights is established through training the neural network on specific training input data. And the activation values of neurons is determined by those weights and the value of the neurons before them. And during the inference process, what's going to happen is that you will propagate input data through a trained neural network to produce, hopefully, the correct output. So those neuron values are going to be updated. I'm going to talk about that in the next slide. And this is really a simple architecture, just to give an idea of the different aspects to consider. But if you want to adapt that to specific problems for different tasks, what you need to do is change the number of layers, the number of neurons per layers, the type of connection, how the neurons are connected together, the non-linearities, so another aspect to talk about in the next slide. So you can really adapt a neural network to different tasks. Now, mathematically, the way the neuron values are determined is by what we call a vector matrix multiplication. So basically, if you want to determine the value of the next layer neurons, so the A neurons, from the input vector X. So you have your input layer, the X neurons. You multiply that input vector by the weight matrix, and that's going to give you the activation value of the neurons on the next layer. Of course, there's another step here, which is you have to apply a nonlinear function. There are multiple types of those linear functions that you can choose from, depending on the model and other considerations. Now, the way this is done traditionally on the hardware is that you will use what we call the digital von Neumann architecture. So you have a processing unit and a memory unit. And if you want to compute the activation values of the neurons, you will have the control unit. Sorry, testing that. You will have the control unit that will send the query to the memory array to retrieve the weights that are stored in this memory array, send them to the the arithmetic logical unit in pink that will then compute the VMM and apply the nonlinear functions. And then you need to send the result back to the memory array to be stored so you can compute the next layer and so on and so on. The issue with that approach is that the data transfer that you have to do continuously is very energy intensive. Also, the speed of this transfer and the capacity of data that you can transfer is, right now it's limited. It's not keeping up with the computational power of AI processor. So you're gonna have a mismatch there at some point. And as I said, this data movement is actually one of the main sources of energy consumption for AI hardware. So a novel hardware paradigm is required if you want to circumvent those bottlenecks. And that's where the analog in-memory computing paradigm comes in. So the way that this works is that instead of storing the memory, the weights separately from the processor, you actually compute the VMM directly on the memory array where you are storing your weight values. And by doing that, you are reducing the data movement and therefore the energy and the latency. The really great way to do that is to actually encode the weight values, so the weight in your neural network, encode them in the conductance states of programmable resistors, which I'll come back to in the next slide. And you arrange those programmable resistors in a crossbar array like this. And if you come back to your Ohm's law and Kirchhoff's law of electrical circuits, you'll see that this type of arrangement can actually compute the vector matrix multiplication in a single step, natively. So if you encode the input vector into voltage values and you send those in the rows of your crossbar array, the output current at each column is going to correspond to the sum of the multiplication of each voltage by each conductance. So that's actually the VMM operation, but in a single step, instead of the digital way, which is like a succession of adders and multipliers. And also, you don't have to move the data around. So much more efficient. Now, the way to actually encode this weight into a device, into a programmable resistor, one of the best ways is using memory stores. So those are resistive memory device. Basically, it's a sandwich of dielectric materials that is specifically engineered. Sorry, losing my voice. And it's in between two metallic electrodes. And if you apply a series of voltage pulses to those electrodes, you will actually create a conductive filament, and you can adjust the conductance of this filament by changing the number of pulses that you apply. So you have a large range of possible analog conductance value that you can set the device to, depending on the pulse number that you apply. So this is really how you would program each of those memory stores in your array to correspond to a specific weight that you want to encode. And the really nice thing about this is that those devices are what we call non-volatile, meaning that they keep their program values without needing to apply a continuous voltage supply. So during the inference process, this doesn't consume any energy, basically. And we're not the only one that are interested in this approach, of course, but at the moment, most, if not all in-memory computing accelerators are actually hybrid. It means that the vector matrix multiplication is performed on this memory store array, but the rest of the computation, like applying the nonlinear functions and routing between different layers, this is done in the digital domain. But this means that you have to have a lot of digital analog and analog digital conversions, and those devices are actually a major source of power consumption. They're really power hungry, and they also add latency. So this kind of negates some of the benefits of the analog approach. And that's why at Irreversible, we actually want to exploit in full the benefits of analog. So we're developing entirely analog neural networks. We're combining this in-memory computing approach with innovative analog circuits that can perform the rest of the computation, so the activation function, the routing, everything, so that we can eliminate the digital analog conversion from the circuit. And in order to do that, we are following a really specific innovation development workflow that includes analog hardware circuit design, performance benchmarking, and some machine learning strategies. And those are all steps that are really essential because there are some particularities to analog hardware that complicates a little bit some things, which is why most people are working on hybrid approach. But we have strategies to circumvent that. 4 minutes? Good. So just to illustrate one of those possible challenge, I'm going to use our proof of concept neural decoder architecture as an example. So this is a relatively small, so that's for the distance tree code, so it's quite small. It's to process the measure syndrome runs from your surface code. And so you give that as an input, and at the output of the neural network, you get a 0 or 1 that indicates if there is a logical error or not, and if you need to correct it. And here, the vector matrix multiplication that happens between to compute the intermediate layer that you see here in your neural network, this is performed on a memory array like that. But what can happen sometimes is that some of those devices are not working properly, they are stuck at fault. So if you actually train your neural network assuming that everything's going to work perfectly, when you actually run it on the hardware, your logical qubit fidelity is going to decrease. That's the green line that you see here, because you're not actually getting the right output. You're not providing the right correction at the output of the neural decoder. So as the faulty device rate increase, your logical fidelity will also decrease. But what we can do is employ a hardware-aware retraining strategy where we include those non-idealities during the training process so that the neural network can learn how to perform well despite those non-idealities. So it becomes robust to them. And you can see here that you recover the near baseline, so the red line, you recover the near baseline fidelity when you use a really specific device-specific retraining. And those are results that you can find in our 2 papers. So I'm going to conclude here. At Irreversible, we're developing this low-energy and low-latency AI hardware for highly constrained use case. This unlocks a lot of really interesting capabilities, especially for sensors and for the edge AI market, with quite interesting benefits that I have listed here. But we remain really involved in the quantum ecosystem with our ongoing quantum-adjacent fundamental research project and some really interesting potential applications in quantum computing and quantum sensing. So you can find us at the Espace Quantique with other companies like Nord Quantique and Pascal. So thank you very much.
So Sophie, Dominique, thank you very much for your presentations. Is there 1 or 2 questions from the audience to either Dominique or Sophie? We have one there. Yep. Can you repeat the question?
Yeah. And then, so the first part was how fast is it to write the weight in the memory? There's actually quite a range depending on a specific device, but it's not super fast. So right now our focus is not, for example, on device training. So we're talking about training digitally and then transferring that, programming it only once on the specific device. What was your second? Oh, yeah, quiet temperature. Yeah, actually, if I remember correctly, so the conductance value will change if you go down in temperature a little bit. All in all, even programming at room temperature, the specific value, there's an error bar there, which is another non-ideal aspect that we can correct for with this hardware-aware retraining strategies.
Well, Sophie, Dominique, thank you very much. If there's questions, I guess that we can keep them for, beer time, just after. Our next speaker is from, whoops, sorry, is from University of Ottawa. Stephanie Cishek is assistant professor at the Department of Physics, and she will talk about smarter quantum experiments boosting quantum research with artificial intelligence. So, Stephanie, it's all yours.
Okay, thanks a lot for the kind introduction. And I would also like to especially thank the organizers for putting this symposium together, and especially for letting me part of it and giving me the chance to tell you a bit about the research that we do in my team in Ottawa. Okay. So let me start with the most important part. So this is my team of students and postdocs. This is the so-called apricot in Ottawa. And all these people work on different projects, but they all kind of address the intersection of AI and quantum science, or quantum science and technologies. And just to clarify it, we are looking at using classical artificial intelligence applied to quantum science and technologies. We are not looking at quantum machine learning. So the main two questions that we address are, does this work? Okay. So how can we enhance quantum science and technologies with artificial intelligence? And can AI somehow tell us how to run quantum experiments more efficiently? And so today I will focus more on this second question, and I will give you some examples where we can use AI to make quantum experiments in general more efficient. So let's start with setting the stage. So we're looking at quantum experiments. I'm a theoretical physicist, so for me a quantum experiment is always some black box that prepares some quantum state. I never understand all the details happening in there, no matter what quantum experiment we are talking about. So I see it as something that can prepare a quantum state, and we can send in some control parameters to prepare some desired quantum state, and we can access the quantum state via projective measurement, so we can read out what state, or kind of what state we have prepared. And so now we can apply AI at all of these three stages. So we can use AI to optimize the control of our quantum system, so to find the optimal control parameters to achieve a desired behavior in our experiment. We can also use AI to autonomously tune or calibrate our quantum experiment into the operational regime. And then in the end, we can even use AI and apply it to the measurement outcome to interpret or evaluate the measurement outcome efficiently. We can actually use AI at all three stages at once, which gives us this end-to-end protocol. But today I will focus on all three stages individually and show you some examples of where we can use AI and how it can make quantum experiments more efficient. So let's start with looking at the optimal control. So this is a project that I'm working on together with my postdoc Logan. And here we are looking at a quantum experiment, and we are looking for determining an optimal set of control parameters to achieve a desired behavior or to solve a given task. So when Logan approached me with this problem, I told him, well, just write down the Hamiltonian, solve it, and you get the optimal control parameters. But apparently this is my naive theoretical view. In experiments, this looks a bit different, because our experimental system is always experiencing some noise behavior, some imperfections, and we would like to find the optimal set of control parameters to achieve a desired behavior, including all the noise and the imperfections that we cannot further specify in our model. And so for this task, we use reinforcement learning. Reinforcement learning is a machine learning algorithm that is commonly used, for example, for game playing, or also for autonomous operation of robots or cars. And it basically uses an agent, and the agent acts in an environment, so it can observe an environment, and it can perform a set, or one out of a set of actions in this environment. And in the end, it is trained to choose an action that, or a set of actions that maximizes a reward that the agent gets. So in the example of game playing, the environment is, for example, the chessboard. The different actions it can choose are the different possible moves. And in the end, it's supposed to find a set of, or a sequence of moves that optimizes the reward of winning the game. So in our example, our agent is an artificial neural network. And thanks to Sophie, I don't need to introduce what an artificial neural network is. She did a great job on this. And so here we have an artificial neural network that takes as an input. Oh, this was the wrong button. Can we restart it? Sorry. Okay, thanks. Okay, so the artificial neural network takes as an input the individual elements of a density matrix that describe a prepared quantum state. And as an output, we get mean and standard deviation values of parameters. So these define a probability distribution underlying a set of parameters. And these are the sets of parameters that define our control sequence. So in our specific example that Logan looked at, we were applying an external field to our quantum system, and we wanted to find the optimal parameters of this external field. And our artificial neural network gave us probability distributions for these 3 parameters that define our external field, so the amplitude, the phase, and the frequency. And so the action that the agent performs is it samples one value for each of the parameters of the external field, it applies it, and it changes the environment, where in our case, the environment is really just the state defined by the density matrix of our quantum system. So the agent observes it again, so performing an action changes the environment, the agent observes it again, and it can predict the next possible action. And it chooses the actions to maximize a reward. So here you can choose any desired figure of merit to maximize. Logan was looking at an example of quantum sensing, where the idea is that we have some unknown parameter in the Hamiltonian underlying our quantum system. And we would like to determine the value of this parameter as precisely as possible by just measuring the state of our quantum system. And so in this case, the figure of merit, or the reward here, is the so-called quantum Fisher information, which is a measure for the sensitivity of our quantum state to changes in this unknown parameter that we would like to determine. Or in other words, if we maximize the quantum Fisher information, we maximize the precision with which we can determine this unknown parameter by really just measuring the state of our quantum system. And so this was our reinforcement learning setup, and Logan had implemented it. And in this paper up here, which will soon appear in PRA, he actually showed that reinforcement learning can successfully optimize such a quantum sensor. So it can really predict a control sequence, which gives us access to an unknown parameter with an optimized precision. But what he also showed, and what is really interesting here, is that this agent can generalize to unseen parameters without retraining. Meaning that if we have our quantum experiment and it experiences some noise, and the noise behavior usually changes over time because the temperature in the lab changes and so on, we actually showed that we don't need to retrain our agent. It can, or is pretty robust to such changes in the noise behavior, which is very powerful thinking about realistic experiments. So we can apply the agent even though the noise behavior changes a bit. Furthermore, it allows us to train the agent on synthetic data, which somehow models the experiment numerically, but it does not need to be an exact model of the experiment. It can be close enough, and the agent will still be able to tell us the optimal control sequence to achieve a desired task. Which was a very nice result, and Logan is still working on a follow-up paper now, so there will be more in this direction coming out soon. But so much about how we use AI for optimizing the control of our quantum experiment. The next part is how we can use AI to autonomously tune our quantum experiment, so the actual experimental setup, into the operational regime. And this part of the talk is based on a project that we did a couple of years ago, and several people from here were involved. So this is the paper that we published. It was together with Michel, Dominique Drouin, Sophie is, I think, also on the paper, if I remember correctly. She's somewhere in the et al. And here we used artificial intelligence or artificial neural networks to autonomously tune quantum dot devices into the operating regime. So a quantum dot device, just to give you a kind of a rough idea how they work. So in our semiconducting quantum dot device, we are preparing a potential landscape that confines the two-dimensional electron gas. And by tuning the potential, we can create such a reservoir of electrons and such a well of electrons, which we call our quantum dot. And then we can tune this potential further, and in the end, we would like to tune it such that we trap a single electron in the quantum dot, which we can then consider as a qubit. And so this tuning of the quantum dot device needs to be done very precisely to really trap a single electron, which is our operational regime. But the behavior is also very device-specific, and so the device needs to be retrained all the time. So a lot of time is spent on really just calibrating the device. But this can actually be done autonomously with artificial intelligence. So to give you an idea of how this works, we can measure the state of our, or the occupation of our quantum dot in a way such that we have such a single electron transistor close to our quantum dot. And on this transistor, we can measure a current. And if we measure the current while tuning the potential in the dot and in the reservoir, we obtain such a stability diagram here. So now you see a big oscillating behavior. This is actually just some background behavior that we are not really interested in. What we are interested in are these very barely visible lines. They're indicated by these arrows there. And these lines are transition lines. And they indicate whenever an electron enters or leaves the quantum dot. And so by detecting these lines, we can actually figure out where we are in the stability diagram. And we can tune our quantum dot device such that we end up in the single electron regime. Okay. So everything we need to do is we need to detect these transition lines. And detecting patterns and images is a straightforward application for artificial neural networks, okay, which can be used to detect these transition lines. All right. So now I have to hurry up a bit. So this is what we looked at. And there are a lot of papers out there on this topic, so this works very successfully. You can automatically tune these devices. There have been follow-up papers coming out right here from Sherbrooke. And currently my student Alex is looking into implementing these autonomous tuning algorithms on specialized hardware, similar to what Sophie has told you about earlier. And this allows us then to actually integrate the entire tuning process in the experimental setup. Okay. So now I have 2 minutes to talk about the last part. So how can we use artificial neural networks, or AI in general, to interpret or evaluate the outcome of our experiment? So how can we deal with the experimental measurement data? Here the motivation is that experimental measurements, or creating experimental measurements, is quite expensive because we always have to re-prepare our state for the next measurement. Our measurements are always destructive. Which can take a lot of time, but at the same time we need a lot of measurements to get a good or accurate estimate of an expectation value. And so our idea is, can we create a digital twin of an experiment, so a numerical model of our experiment that behaves in the same way, and with this allows us to efficiently create synthetic data. And so the way it works is that we have our quantum experiment, and then we can send the measurement data into a so-called generative artificial neural network. And these networks are known for being able to implement or encode probability distributions, and they allow us to draw samples from them. And this is the principle underlying any text or image generation, like ChatGPT does exactly this. And so now we want to train our neural network to encode the density matrix underlying our measurement data. Once we have done this, we can create more data following the same distribution, and this gives us a better estimate of observables. And so in this case, this neural network would be our digital twin. So it would really be a numerical model of our experiment, and would also include the entire noise and imperfection behavior of our experiment. It would literally copy the behavior of the experimental setup. And so this is a project that I'm looking into together with my students Risa and Zachary at this time. So we are trying to find an optimized and efficient algorithm to create such digital twins. And we are collaborating with Jeff Landin, who has a photonics lab in Ottawa. So ideally, we will try out all these algorithms on his experiments. Just on a last note, you can use the same neural network representation or encoding of quantum states. And instead of training it on experimental data, you can actually train it to minimize the expectation value of a given Hamiltonian. And this allows you to variationally find a ground state representation in your neural network of some given Hamiltonian. And together with my former student Kyle, we have shown in this paper down there that this allows us to actually model ground states of enormous quantum systems very accurately. So it gives us a good theoretical understanding of quantum systems. And so Faith, my current PhD student, is driving this further and further optimizing the neural networks right now. So with this, I'm at the end of my presentation. I think the take-home message is that AI promises several enhancements to quantum experiments. We have a lot of tools, so if you find any applications of our tools in your setups, please contact me. We are happy to try them out on actual experimental data. And so I'm leaving you with just highlighting the other projects that are going on these days in my research team. Thank you.
Fantastic. Thank you very much, Stephanie. We'll, once again, keep the questions for just after. We have one last presentation for the day. And I invite on stage Hiro René Coiffarte. Not she, but he is a PhD candidate at the Department of Mathematics here at University of Sherbrooke. He will talk about Kubo-based optimization in regression trees for modeling reserves in property and casualty insurance. So, Hiro, this is all for you.
Okay. Ok, et pour avancer, c'est juste le gros bouton. Ok. Hi everyone. It's a pleasure to present a Kubo formulation in CAT algorithm. I'm a PhD student in mathematics, and we are interested to the application of quantum computing in insurance. That's why we talk about CAT algorithm. The first problem we find in insurance is the optimization problem in the CAT algorithm. The outline of my presentation is first we will motivate the problem based on quantum computing and optimization. In the second step, we will discuss about the background of the CAT algorithms. And in the third point, we will give some objectives and the proposed methodology to solve a CAT algorithm using Kubo. In the first step, we will give a real Kubo formulation of the optimization problem and finish by conclusion and ongoing work. Recent year, the quantum computing offers new ways to solve optimization problems. And the most framework in mathematical framework for quantum computing is Kubo. Kubo means quadratic and constrained binary optimization. This framework is particularly suited for quantum algorithms such as the quantum annealing, the QOA, quantum approximate optimization algorithm. So, if we can reformulate the classical optimization problem as a Kubo, we can solve them using the quantum solver or classical solver or hybrid solvers. That motivates this research. For the first step, we need to introduce the CAT algorithm. Classification and regression tree is the most important algorithm in machine learning because it offers a simplicity and interpretability. It also has a good balance between accuracy, flexibility, and transparency. A CAT algorithm builds a binary decision tree by applying successive splitting split data set. That means at each node, the decision of splitting is the result of an optimization problem that determines the way to split the data efficiently. Now we can introduce the node splitting optimization problem in the CAT. If I consider X, the same problem. If X is a explanatory vector of explanatory variables, Y the response variables, given a node with n observation, the goal is to split this node into two child nodes. And then we define the gain of cost function phi for the candidate split data by this expression. Data phi is equal of the expected value of the cost function in the original nodes minus the weighted expected value of the cost function in the resulting child nodes. The goal is to find the best way to split split the data, and we check the best split data star that maximizes this gain function or improvement. In a classical regression task, that means the optimal splitter is given by this minimization problem, since in the original problem, this part is constant for each node. This part is constant, and then the optimal problem resulting is to minimize this problem. For numerical variables, this optimization is not complicated, is work well. But when we work with categorical variables, that's become more complicated because for categorical variables, the number of possible splits is grow exponentially. Then the exact solution become computationally intensive for categorical variables and for the larger data set. So some implementation of COT algorithm use of heuristic, and this heuristic can lead to the local optima. This local optima and therefore lead to the suboptimal splits. We propose here to reformulate the cubo splitting, the low splitting optimization step in CAT as a cubo problem, and solve it efficiently using quantum algorithm or quantum solvers. The proposed methodology is in 4 steps. First, we will express the problem in the fractional form using variance identity. In the second step, we reformulate the fractional form as cubo problem using Dinkelbach method, and solve it using a hybrid solver or quantum solver. In the next step, in the final step, we will integrate cubo into the CAT algorithm process. Today, I will present the two points of this methodology because I don't have the time. Let's start for the reformulation of the optimization problem. The starting point of this step is the variance identity, which expresses the variance as a pairwise difference in the value of observation in the response variables. In this formula, we don't have a mean. We avoid the computation of the mean. So using this formulation of the variance and the original optimization problem, we can formulate the fractional form of the problem that is given was this optimization problem. For moving from the fractional form to the cubo problem, we need to transform this ratio as a cubo problem. Since cubo is defined by this optimization problem, where we have equivalence between the standard formulation of cubo and the matrix formulation. In this formulation, x, y is a binary variables, and q is a symmetric problem. We have a fraction, we need to transform it into the quadratic formulation of the problem. To do so, we use the Dinkelbach method. This method transforms the original problem P here, ratio, to the equivalent parametric formulation F lambda here. And based on the result of U and U 2014, who give equivalence between the optimal solution lambda x star to the original problem and the optimal solution x star in the parametric problem. Using this equivalence, we develop an anti-iterative Newton-based method on lambda. So for each lambda, we can have a solved problem P lambda k that is expressed in cubo, and we can update lambda recursively until convergence. Now we can introduce the binary encoding of category and splits. In our work, we define the category of the explanatory variable as a classes C alpha. And we define a binary variables Q alpha as Q alpha is equal 1 if my class C alpha belong to the left node, and 0 if it belongs to the right node. That helps us to have a binary variables. And using this binary encoding, we can express the weighted variance of each child node using this expression here. We have the weighted variance in the left node and the weighted variance in the right node. Here we express it using the binary variable Q alpha, Q beta, and V alpha beta. V alpha beta is a pairwise difference in the response variable observation, and it can be pre-computed before input in the cubo. We can also express the number of observations in each child node using Q alpha and N alpha. Using this formula, weighted variance formula, and the iterative Jenkins-Bash method, we define the iterative gain in the cost function. The iterative gain in the cost function is given by this expression, where in my expression, I have the quadratic term here and the linear term. This expression depends on the lambda. That's why we talk about the iterative gain function, because we have iteration to handle this problem. And finally, the Kubo formulation of the CAT algorithm optimization problem is given by this optimization problem, where the quadratic term Q alpha beta and the linear term L alpha beta are defined by this equation here. We use the GRuby classical solver to solve this optimization problem, but we don't have the time to show the results today. So, to conclude, we first reformulate the split optimization step in decision tree as a learning Kubo problem, and we solve it using the Kubo solver. For the next step, we need to introduce the Kubo formulation in the CAT algorithm to build the Kubo decision tree, and we will apply this decision tree to the real-world micro-level, claim-level data for individual reserving. We will also do the benchmark and compare the performances with another algorithm, classical algorithm in CAT. And finally, we will explore the integration of hybrid or quantum algorithm and solver in this Kubo splitting that can lead us to build a quantum Kubo-based decision tree for insurance. I'm at the end of my presentation. Thank you for your attention.
Thank you very much, Hiro. Well, this is now the end of the day. I would like to thank you all for either being here today or being present online. Thank you also to all our presenters of the day and panelists. I guess this was an incredible day in terms of information, exchange of ideas, and really, well, thank you all. I would also like to thank Tom Mala, who's behind all the logistics of the day. I've received communications from him. He was here all day for things to run smoothly. So thanks a lot, Tom. Maybe a big round of applause for you. And, well, I now invite you to the cocktail part of the day. We also have a poster session with many exciting, more, well, research projects to be presented over these posters. So, well, please join me over there. Thanks a lot.
Merci.